Hello, wonderful people. Welcome back to another journey through the cosmos, where tonight we're going to explore something truly extraordinary. Get comfortable, dim the lights, and let's drift together into the universe's most extreme phenomena. Imagine a star so massive that when it dies, it doesn't just fade away. Instead, it compresses matter to densities so extreme that a single teaspoon would weigh as much as Mount Everest. A stellar corpse spinning hundreds of times per second, with magnetic fields powerful enough to disintegrate atoms from thousands of miles away. These aren't theoretical objects from science fiction. They're neutron stars, and they exist at the very edge of what physics allows. Tonight we're going to understand how these cosmic monsters are born, what they're made of, and why they might be the universe's most fascinating laboratories for understanding reality itself. Before we dive deeper into this cosmic wonder, if you're enjoying this journey through the stars, give this video a like. It helps more people discover the mysteries of our universe. And if you haven't subscribed yet, consider joining our community of curious minds who love exploring the cosmos together. Your support means everything. Now, let's begin our story, where all great cosmic tales start with death. But not just any death. We're talking about the most violent explosion the universe can produce. On July 4th, 1054, AD, Chinese astronomers witnessed something that would puzzle humanity for nearly 1,000 years. They recorded what they called a guest star in the constellation Taurus, a celestial visitor so bright it could be seen during the day for 23 consecutive days. For weeks, this mysterious light outshone every star in the night sky. Then gradually, it faded from view. The imperial astronomers meticulously documented this event in the Sung Shiu, the official history of the Sung dynasty, calling it a phenomenon of great auspiciousness. They had no idea they were witnessing the birth of one of the universe's most extreme objects. What those ancient observers saw was a supernova, the catastrophic death of a massive star. But the story doesn't end with that brilliant flash of light. When modern astronomers turned their telescopes toward those same coordinates in Taurus, they found something remarkable. The Crab Nebula, an expanding cloud of gas and debris still glowing from that explosion nearly a millennium ago. And at the very center of this cosmic wreckage, hidden within the chaos, sits something even more extraordinary. A neutron star, the compressed core of the original giant, now spinning 30 times per second, is a stellar lighthouse that has been beaming radiation across the galaxy for the past 1,000 years. But how does a star transform into something so fundamentally different from what it once was? To understand this, we need to explore the violent physics of stellar death. Stars spend their lives in a constant battle between two opposing forces. Gravity relentlessly pulls matter inward, trying to collapse the star. Nuclear fusion in the core pushes outward, generating the pressure and energy that keeps the star inflated. For millions or even billions of years, these forces remain balanced. The star shines steadily, burning through its nuclear fuel in a cosmic equilibrium. But this balance cannot last forever. When a massive star, typically between 8 and 20 times the mass of our Sun, exhausts its nuclear fuel, the game changes dramatically. Without fusion to generate outward pressure, gravity wins. And it doesn't just win gradually. The core collapses in less than a second, falling inward at nearly a quarter the speed of light. To give you perspective, imagine the entire mass of our Sun, which is so vast that it makes up 99.86% of our solar system's total mass, compressed into a sphere about the size of Manhattan in just fractions of a second. The temperatures spike to hundreds of billions of degrees. The density becomes so extreme that atomic structure itself begins to break down. Here's where the physics becomes almost unimaginable. Under normal circumstances, atoms are mostly empty space. The nucleus occupies only a tiny fraction of an atom's volume. But during this collapse, electrons are forced into the atomic nucleus, combining with protons to form neutrons through a process called neutronization. What remains is matter composed almost entirely of neutrons packed together so tightly that they touch each other. There's no empty space left, no atoms as we understand them. Just an ocean of neutrons pressed together by gravity into a sphere typically just 12 miles across. This is a neutron star matter compressed to the absolute physical limit before it would collapse further into a black hole. The energy released during this core collapse is staggering. In just a few seconds, a dying star releases more energy than our sun will produce in its entire 10 billion year lifetime. Most of this energy, about 99%, escapes as neutrinos, ghostly particles that barely interact with matter and stream out into space at the speed of light. But that remaining 1% is more than enough to blow apart the star's outer layers in a spectacular supernova explosion. This is what those Chinese astronomers saw in 1054, not the star itself, but the shockwave of its death throes expanding outward and lighting up the cosmos. Now, you might be wondering, why doesn't every star become a neutron star when it dies? This is where stellar mass becomes crucial. Stars less than about 8 solar masses don't have enough gravitational force to trigger this extreme collapse. They end their lives more gently as white dwarfs, Earth-sized stellar embers that slowly cool over billions of years. But there's also an upper limit. Stars more massive than roughly 20 to 25 solar masses don't stop at the neutron star stage. Their cores are so massive that even neutron degeneracy pressure, the quantum mechanical force that holds neutrons apart, cannot resist gravity's pull. These giants collapse all the way into black holes, creating space-time singularities, where our understanding of physics breaks down completely. So, neutron stars occupy a sweet spot in the cosmic mass range, massive enough to overcome atomic structure, but not quite massive enough to become black holes. They exist at the threshold, right at the edge of what the universe permits. Let's talk about a star you've probably heard of, Betelgeuse. This red supergiant in the constellation Orion is one of the brightest stars in our night sky. It's also a ticking time bomb, with a mass estimated between 15 and 20 times that of our sun. Betelgeuse sits squarely in the neutron star formation zone. Astronomers know that sometime in the next 100,000 years, maybe tomorrow, maybe in 50 millennia, Betelgeuse will exhaust its nuclear fuel and undergo core collapse. When it does, it will create one of the most spectacular supernovae visible from Earth in recorded history. For several weeks, it will shine brighter than the full moon, visible even during daylight hours. And when the fireworks fade, there will almost certainly be a neutron star at the center of the expanding debris cloud, the compressed heart of this stellar giant left behind, as a cosmic monument to one of nature's most violent transformations. The discovery of neutron stars fundamentally changed our understanding of matter itself. Before their theoretical prediction in the 1930s and observational confirmation in the 1960s, scientists didn't fully appreciate just how extreme the universe could be. We thought we understood the limits of density pressure and gravitational force. Neutron stars shattered those assumptions. They revealed that the universe contains natural laboratories where matter exists in states we cannot recreate on Earth, where physics operates at the absolute boundary of what's theoretically possible. Think about this for a moment. The matter inside a neutron star is denser than an atomic nucleus. In fact, a neutron star is essentially one giant atomic nucleus held together by gravity instead of the strong nuclear force. If you could somehow scoop up a teaspoon of neutron star material and bring it to Earth, it would weigh approximately 6 billion tons. That's roughly the mass of Mount Everest, or about 900 Great Pyramids of Giza, all compressed into something you could hold in your hand. Of course, this is purely hypothetical. If such material could exist outside the intense gravitational field of a neutron star, it would instantaneously explode with the force of thousands of nuclear weapons. But the thought experiment helps us grasp just how alien these objects truly are. The formation of a neutron star is not a smooth or uniform process. As the core collapses, it doesn't fall inward symmetrically. Turbulence, magnetic fields, and rotation create asymmetries that persist in the final object. This is why neutron stars often have incredibly strong magnetic fields and why they can spin at phenomenal rates. When a massive star collapses to a tiny fraction of its original size, the conservation of angular momentum means its rotation speed increases dramatically. It's the same principle that makes figure skaters spin faster when they pull their arms inward, but taken to a cosmic extreme. A slowly rotating giant star taking weeks to complete one rotation becomes a neutron star, spinning dozens, hundreds, or even over 700 times per second. These aren't abstract numbers. They represent physics pushed to its absolute limit. A neutron star spinning at 700 rotations per second means that material at its equator is moving at roughly 10% the speed of light. Any faster, and the star would tear itself apart, flinging matter into space despite the tremendous gravitational force trying to hold everything together. Neutron stars exist right at this threshold: maximum density, maximum spin, maximum magnetic field. Strength, everything about them represents nature, operating at the very edge of possibility. The death of massive stars and the birth of neutron stars also plays a crucial role in cosmic chemistry. During the supernova explosion, the intense heat and pressure create conditions perfect for nuclear fusion beyond what occurs in stellar cores. Elements heavier than iron, which cannot be produced through normal stellar fusion because they require energy input rather than releasing it, are forged in these few seconds of extreme violence. Gold, platinum, uranium, thorium, all the heavy elements that exist in nature are created in supernova explosions and neutron star mergers. The gold in your jewelry, the uranium in nuclear reactors, the rare earth elements in your smartphone. All of these atoms were forged in stellar deaths. You are literally wearing and using the remnants of ancient supernovae. The universe recycles itself, and neutron stars are the factories where the heaviest materials are produced. As we close this first chapter of our journey, consider the incredible transformation we've explored. A star that once shone peacefully for millions of years, fusing hydrogen into helium in its core, maintaining a delicate balance between gravity and pressure, suddenly runs out of fuel. In less than a second, its core implodes with unimaginable violence. Atoms are crushed out of existence, transformed into a sea of neutrons, packed together with no space between them. The outer layers are blasted into space, enriching the cosmos with heavy elements. And what remains is an object so dense, so extreme, that it challenges our fundamental understanding of matter and physics. We've witnessed the birth. We've seen how giants collapse and transform into something utterly alien. But the story of neutron stars is just beginning. Because these cosmic objects aren't just dense remnants of dead stars, they're active, dynamic, and stranger than we ever imagined. In our next section, we're going to dive deeper into the heart of a neutron star and explore what happens when matter is pushed beyond the atomic structure we're familiar with into a realm where the rules of physics become increasingly bizarre and beautiful. The journey into the densest matter in the universe awaits. So, we've witnessed the violent birth, the catastrophic collapse that creates these cosmic monsters. But now comes the truly mind-bending question: what exactly is a neutron star made of? Because when we peer into the heart of these objects, we're not just looking at compressed matter. We're looking at a state of existence that defies everything we understand about the physical world. Imagine matter so dense that the very concept of empty space ceases to exist, where electrons and protons are crushed together into something fundamentally different, where the distinction between particle and nucleus blurs into irrelevance. This is neutron star matter, and it represents the most extreme substance in the observable universe. If you're finding this journey through cosmic extremes as fascinating as I am, take a moment to hit that like button. It genuinely helps this content reach fellow space enthusiasts who share our curiosity about the universe's mysteries. And if you're new here, subscribe and join us as we continue exploring the cosmos together. Let's start with a comparison that might help ground this abstract concept in something tangible. You know what a teaspoon looks like? small enough to stir your coffee to measure out sugar, something utterly ordinary and familiar. Now, imagine filling that teaspoon with neutron star material. That tiny volume, maybe 5 milliliters, would weigh approximately 6 billion tons. To put that in perspective, that's more than the combined weight of every single human being on Earth, all 8 billion of us, crammed into something you could hold between your thumb and forefinger. It's the mass of Mount Everest, the tallest mountain on our planet, compressed to fit in your palm. This isn't science fiction exaggeration. This is the verified, measured reality of neutron star density. But these comparisons, while striking, still don't capture the truly alien nature of what we're dealing with. To really understand neutron stars, we need to go deeper down to the quantum level, where the familiar rules of matter begin to break down entirely. Under normal circumstances, atoms are mostly nothing. The nucleus occupies only about 1/1,000,000th of an atom's total volume. The rest is empty space, or more accurately, the probabilistic cloud where electrons might be found. This emptiness is why you can walk through air, why solid objects aren't actually solid at the quantum level, why matter as we know it has the properties it does. But in a neutron star, this fundamental architecture of reality is obliterated. During the core collapse we discussed earlier, something remarkable happens through a process called neutronization. As gravity compresses matter to unimaginable densities, electrons are forced into atomic nuclei, where they combine with protons in a reaction mediated by the weak nuclear force. An electron plus a proton yields a neutron and a neutrino. The neutrino escapes at light speed, carrying away energy and leaving behind the neutron. This process repeats trillions upon trillions of times in the collapsing core. What emerges is matter with almost no protons, almost no electrons, just an ocean of neutrons packed together so tightly they're essentially touching. The empty space that defines normal matter has been completely eliminated. This is why we call them neutron stars. They're not really stars in any meaningful sense. They're gigantic atomic nuclei held together by gravity instead of the strong nuclear force. Now, here's where it gets even stranger. A neutron star isn't uniform throughout. Despite being only about 20 kilometers in diameter, roughly the size of a small city, these objects have distinct layers, each with radically different properties. And understanding this internal structure has been one of the great challenges of modern astrophysics, because we can't exactly crack one open and look inside. Everything we know comes from theoretical physics computer simulations and careful observations of how neutron stars behave. The outermost layer, paradoxically, is the most normal. The crust of a neutron star, extending down about 1 kilometer from the surface, consists of actual atoms, primarily iron-56, the most stable atomic nucleus. But even here, nothing is truly normal. The atoms are arranged in a perfectly crystalline lattice, locked in place by gravitational pressure millions of times stronger than anything on Earth. The density at the surface is roughly 1 million times denser than the densest materials we have on our planet. Imagine walking on a surface where each cubic centimeter weighs about 1 million grams or 1 ton. The crust is essentially a solid metal ocean of iron, but compressed to densities that make Earth's core seem like cotton candy by comparison. As we descend deeper into the neutron star, past about 1/2 kilometer, we enter what's called the inner crust. And this is where things become truly exotic. Here, the atomic nuclei are packed so closely that free neutrons begin to drip out of them, forming a neutron gas that permeates the spaces between nuclei. Physicists call this neutron drip, and it marks the transition from conventional nuclear matter to something unprecedented. The density has now reached 100 trillion grams per cubic centimeter. At this depth, atomic nuclei themselves begin to deform under the crushing pressure, creating bizarre shapes. Computer simulations suggest these nuclei might arrange themselves into long rods, flat plates, or even twisted tunnel structures that physicists have nicknamed nuclear pasta spaghetti lasagna and other culinary terms for these exotic configurations of matter. But the truly mind-bending region lies deeper still. Beyond about 1 kilometer down, we enter the outer core where the density exceeds that of atomic nuclei themselves. Here, individual nuclei can no longer exist as separate entities. They merge into a uniform fluid of neutrons, with a small percentage of protons and electrons mixed in to maintain electrical neutrality. This is neutron star matter in its purest form, a state of matter that doesn't exist anywhere else in the universe, except possibly in the hearts of other neutron stars, and in the first microseconds after the Big Bang. The density has now reached several times nuclear density, somewhere between 100 million and 1 billion tons per cubic centimeter. And then there's the core itself, the innermost region. And this is where our understanding becomes genuinely uncertain. At the very center of a neutron star, densities might reach 10 times nuclear density, or even higher. And at these extremes, physicists honestly don't know what happens. Several competing theories exist, and this uncertainty represents one of the most exciting frontiers in modern physics. One possibility is that the matter remains composed of neutrons, protons, and electrons just at increasingly extreme densities. But there are more exotic possibilities that read like science fiction, yet are taken seriously by theoretical physicists. One hypothesis suggests that at sufficient density, neutrons themselves might break apart into their constituent quarks. In normal matter, quarks are always confined inside protons and neutrons never existing freely. But in the core of a neutron star, the pressure might be so intense that this confinement breaks down, creating what's called quark matter. This would be a soup of up quarks, down quarks, and strange quarks all swimming freely in a deconfined state. If this is true, the cores of neutron stars might actually be quark stars, objects composed of liberated fundamental particles, rather than composite particles like neutrons. Another intriguing possibility involves hyperons, exotic particles that contain strange quarks and are heavier than ordinary protons and neutrons. Under extreme pressure, it might become energetically favorable to convert ordinary neutrons into these heavier hyperons. This would create a hyperon star with a core composed of particles that only exist for fleeting moments in particle accelerators here on Earth, yet stable inside neutron stars due to the immense gravitational pressure. Or perhaps the core contains a mixture: conventional neutron, matter quark matter, and hyperons, all coexisting in different layers or phases like oil and water, refusing to fully mix even under these extreme conditions. Why does this uncertainty matter? Because the exact composition of neutron star cores determines something called the equation of state, a mathematical relationship between pressure and density. And the equation of state directly affects observable properties like the maximum mass a neutron star can have before collapsing into a black hole, and the relationship between a neutron star's mass and its radius. By making precise measurements of neutron star masses and sizes, astronomers can actually test these different theories about what lies at the heart of these objects. It's a beautiful example of how observation and theory work together in physics. We can't look inside a neutron star directly, but we can measure its external properties with enough precision to rule out certain compositions and favor others. This is where missions like NICER, the Neutron Star Interior Composition Explorer, aboard the International Space Station, become crucial. NICER uses X-ray observations to measure the sizes of neutron stars with unprecedented accuracy. By watching how X-rays from hotspots on the neutron star's surface change as the star rotates, scientists can determine not just the star's radius, but also map slight distortions in space-time caused by its intense gravity. These measurements are helping us narrow down which theoretical models match reality, bringing us closer to understanding what matter does under the most extreme conditions the universe permits. One of the most common misconceptions about neutron stars is that people confuse them with black holes. It's an understandable mistake. Both are incredibly dense remnants of dead stars. Both have intense gravitational fields. Both are invisible to traditional optical telescopes, but they're fundamentally different objects. A black hole is a region where gravity has become so strong that space-time itself has ruptured, creating a singularity where our current physics breaks down completely. Nothing, not even light, can escape once it crosses the event horizon. A neutron star, while incredibly dense, still has a surface. Light can escape. Matter can exist in its vicinity without being inevitably pulled in. You could at least in principle stand on a neutron star's surface, though the experience would be lethal in countless ways. But you could not stand on a black hole because a black hole has no surface to stand on in any meaningful sense. The crucial difference is that neutron stars exist just barely on the right side of the gravitational threshold, while black holes have crossed that boundary into something fundamentally different. There's also a common misunderstanding about what would happen if you could hold neutron star matter in your hand. People sometimes imagine that, because it's so dense, it would be incredibly heavy, but otherwise behave like a normal substance. This couldn't be further from the truth. Neutron star matter only remains stable under the immense gravitational pressure inside a neutron star. Remove it from that environment, and it would instantly expand with catastrophic violence. The neutron degeneracy pressure that holds neutrons together against gravity would cause the material to explode outward, releasing energy equivalent to thousands of nuclear weapons in a fraction of a second. Neutron star matter is a high-pressure phase of matter that literally cannot exist at normal pressures, much like how the exotic forms of ice that exist in the depths of Jupiter simply cannot exist at Earth's surface pressure and temperature. The study of neutron stars teaches us profound lessons about the nature of matter itself. For over a century, we've been probing deeper into the structure of atoms, discovering electrons, then nuclei, then protons and neutrons, then quarks and gluons. We've built massive particle accelerators, like the Large Hadron Collider, to smash particles together at enormous energies, recreating for fleeting instants the conditions that existed microseconds after the Big Bang. But neutron stars are natural laboratories that reach energies and densities we can't achieve artificially. They're showing us what matter does when pushed beyond anything we can recreate on Earth. They're testing our theories of nuclear physics, quantum mechanics, and general relativity simultaneously, in conditions that combine extreme density, extreme magnetic fields, and extreme gravity all at once. Perhaps most remarkably, neutron stars reveal that the universe has phases of matter we've barely begun to understand. We're familiar with solids, liquids, gases, and plasmas, but neutron star matter represents something entirely different, a form of matter, where the distinction between particle and bulk substance becomes meaningless, where quantum effects operate on macroscopic scales, where the very fabric of space and time is warped by the presence of mass. These objects force us to expand our conception of what matter can be, what states of existence are possible in our universe. As we contemplate these cosmic extremes, it's worth pausing to appreciate how far human understanding has come. Less than a century ago, we didn't know neutron stars existed. We couldn't have predicted them because we didn't understand nuclear physics well enough. Today, we're not only studying these objects from millions of light years away, we're using them to probe the fundamental laws of physics to test Einstein's theory of general relativity in regimes he never imagined to explore, states of matter that push quantum mechanics to its limits. Neutron stars are simultaneously the universe's densest matter and humanity's clearest window into the deep structure of reality. But density and composition are only part of the neutron star story, because these objects don't just sit quietly in space. They announce their presence in the most dramatic way possible by becoming cosmic lighthouses that sweep beams of radiation across the galaxy with clockwork precision. Understanding how and why neutron stars do this will reveal yet another layer of their extraordinary nature. The story of their discovery is one of the most fascinating chapters in modern astronomy, involving mysterious signals, scientific controversy, and a discovery that would reshape our understanding of the cosmos. Picture this. It's July 1967, and a young graduate student at Cambridge University is analyzing chart recordings from a new radio telescope. She notices something peculiar, a repeating signal so regular, so precise that it seems almost artificial. The pulses arrive every 1.337 seconds, never varying by more than a few millionths of a second. Her supervisors are skeptical. Radio interference, they suggest. A glitch in the equipment. But Jocelyn Bell Burnell knows better. She's discovered something that will revolutionize our understanding of the universe. Something so unexpected that the research team half-jokingly labels it LGM-1 Little Green Men. 1 because the signal's precision seems almost too perfect to be natural. What she'd found wasn't aliens. It was something even more extraordinary, the first pulsar, a neutron star, announcing its presence through the cosmos, with the regularity of the universe's most precise clock. If this story of cosmic discovery is captivating, you show some love by hitting that like button. Every like helps the algorithm share these astronomical wonders with more curious minds. And if you haven't already subscribed to join our cosmic community, there's so much more to explore together. Jocelyn Bell's discovery is one of the most remarkable stories in modern astronomy, not just for what was found, but for how it unfolded. The telescope she was using wasn't designed to hunt for pulsars, because nobody knew pulsars existed. It was built to study quasars, distant galaxies with active supermassive black holes. The instrument consisted of over 2,000 dipole antennas arranged in a field covering 4.5 acres, connected by 120 miles of wire and cable. Bell's job as a graduate student was to analyze the paper chart recordings, produced by this telescope, miles and miles of squiggly lines tracking radio signals from space. It was tedious work, the kind of task that would make most people's eyes glaze over. But Bell was meticulous, and her attention to detail paid off in a way that would change science forever. In July 1967, she noticed what she later called a bit of scruff on the recordings, a brief burst of radio emission that didn't look like the usual interference or astronomical sources. Most researchers would have dismissed it. Radio telescopes pick up all kinds of terrestrial interference broadcasts from radio stations, electrical equipment passing vehicles. But Bell was intrigued. She started monitoring that patch of sky more carefully. And in November, she caught the signal again. This time, she saw what made it truly remarkable. The signal wasn't random noise. It was a series of pulses, each lasting a mere 0.016 seconds, repeating with astonishing regularity every 1.337 seconds. The precision was breathtaking. Natural astronomical phenomena simply didn't behave like this. Stars fluctuate, gas clouds are chaotic. Even the most regular astronomical objects vary over time. But this signal was rock-steady, pulse after pulse after pulse, like a cosmic metronome, beating with unwavering rhythm. Bell brought the discovery to her supervisor, Anthony Hewish, and the team began a serious investigation. The first question was whether this could possibly be artificial, perhaps a signal from an extraterrestrial civilization. It sounds far-fetched, but the regularity of the pulses genuinely suggested an artificial origin. The team even privately referred to the source as LGM-1 for Little Green Men. But several factors argued against the alien hypothesis. First, the signal showed no Doppler shift, meaning it wasn't coming from a planet orbiting a star, which any technologically advanced civilization presumably would inhabit. Second, and more definitively, Bell soon discovered 3 more similar sources in completely different parts of the sky, all pulsing with the same regularity but different periods. It seemed implausible that multiple alien civilizations would all be broadcasting signals with the same characteristics. Yet the odds of these being natural phenomena seemed equally remote. The breakthrough came when astronomers realized what they were actually observing. The pulses weren't the object turning on and off. They were caused by a lighthouse effect. Imagine a lighthouse on a rocky shore. The light itself shines continuously, but from your perspective on a distant ship, you see a flash every time the rotating beam sweeps across your position. Pulsars work exactly the same way. The neutron star emits beams of radiation from its magnetic poles, and as the star rotates, these beams sweep across space. When a beam happens to point toward Earth, we detect a pulse. When it points elsewhere, we detect nothing. The pulse period we observe is simply the rotation period of the neutron star. But here's what made this discovery so shocking. For an object to pulse every 1.337 seconds, it must complete one full rotation in that time. Now stars are huge. Our sun takes about 25 days to rotate once at its equator. Larger stars rotate even more slowly. If something the size of a normal star tried to spin once per second, centrifugal force would tear it apart. The material at the equator would be flung into space, unable to stay gravitationally bound. For an object to rotate this fast and remain intact, it has to be incredibly small and incredibly dense. The only theoretical object that fit these requirements was a neutron star, the collapsed cores we've been discussing. Suddenly, pulsars weren't just mysterious radio sources. They were the observational confirmation of neutron stars objects that had been theoretically predicted in the 1930s but never actually seen. The discovery was so significant that it won the Nobel Prize in Physics in 1974. But here's where the story takes a controversial turn. The prize was awarded to Anthony Hewish and Martin Ryle for the development of radio astronomy techniques, with Hewish specifically cited for his decisive role in the discovery of pulsars. Jocelyn Bell, who actually detected the first pulsar and whose careful analysis made the discovery possible, was not included. To this day, many astronomers consider this one of the Nobel Prize's most egregious oversights. Bell herself has been gracious about the matter, noting that as a graduate student at the time, she was in a junior position. But her contribution was fundamental, and most historians of science agree she deserved recognition. The episode highlights a broader issue in science: how collaborative discoveries are credited, and particularly how women, scientists, have historically been overlooked for their contributions. Now, let's dive into the physics of how pulsars actually work, because it's a beautiful intersection of rotation, magnetism, and relativity. When a massive star collapses into a neutron star, two things are conserved: angular momentum and magnetic field flux. Angular momentum conservation is why neutron stars spin so fast. A slowly rotating giant star becomes a rapidly rotating tiny star, just like a figure skater spinning faster when pulling their arms inward. But the magnetic field amplification is equally dramatic. The original star might have had a relatively weak magnetic field comparable to Earth's, or perhaps a bit stronger. But when the star's radius shrinks by a factor of 100,000, the magnetic field strength increases by a factor of 10 billion. This creates magnetic fields that are among the strongest in the universe, typically 1 trillion times stronger than Earth's magnetic field. These intense magnetic fields play a crucial role in how pulsars emit radiation. Charged particles, primarily electrons and positrons, are accelerated to enormous energies along the magnetic field lines. As these particles spiral around the field lines near the magnetic poles, they emit radiation across the electromagnetic spectrum: radio waves, visible light, X-rays, even gamma rays. But crucially, the magnetic poles of a neutron star usually aren't aligned with its rotation axis. Just like Earth's magnetic North Pole isn't exactly at the geographic North Pole. This misalignment is what creates the lighthouse effect. As the neutron star rotates its magnetic poles and the associated radiation beams sweep through space, if one of these beams happens to intersect Earth, we see a pulse each time it sweeps past us. The variety of pulsars we've discovered is astonishing. Some pulse hundreds of times per second, others just once every few seconds. Some emit primarily radio waves, others are brightest in X-rays or gamma rays. Let me tell you about PSR J1748246AD. which holds the record as the fastest spinning pulsar we've ever found. This remarkable object, located in the globular cluster, Terzan 5, spins at an absolutely mind-boggling 716 rotations per second. Now think about that for a moment. This is an object with more mass than our Sun, compressed into a sphere about 20 kilometers across, completing 716 full rotations every single second. The equator of this neutron star is moving at approximately 24% the speed of light. We're talking about matter moving at 72,000 kilometers per second, a significant fraction of the ultimate cosmic speed limit. If this neutron star were spinning just slightly faster, centrifugal force would overcome gravity, and the star would tear itself apart despite its intense gravitational field. How can anything rotate that fast without flying apart? The answer lies in the incredible strength of neutron star material and the intense gravity holding everything together. Remember, we're talking about matter at nuclear density, effectively one giant atomic nucleus held together by gravity. The structural strength is phenomenal, but even neutron stars have limits. Theoretical calculations suggest the absolute maximum rotation rate for a neutron star is somewhere around 1,000 to 1,500 rotations per second, depending on the star's mass and equation of state. Faster than that, and even neutron degeneracy pressure can't prevent the star from being torn apart by centrifugal force. The fact that we have found pulsars spinning at 7 and 16 times per second tells us we're observing physics operating very close to its absolute limits. Different types of pulsars reveal different aspects of neutron star behavior. Radio pulsars like the ones Bell discovered are powered by their rotation. As the neutron star spins down over millions of years, it gradually loses rotational energy, and this energy powers the radio emission. Eventually, after tens or hundreds of millions of years, the neutron star slows down enough that it can no longer generate strong radio beams, and it becomes invisible to radio telescopes, a dead pulsar. But that's not the end of the story, because neutron stars and binary systems can be spun back up again through a process called accretion. If the neutron star has a companion star, it can pull matter off that companion. This infalling matter carries angular momentum, and as it spirals onto the neutron star, it spins the star back up to incredible speeds, creating what we call millisecond pulsars, recycled neutron stars given a second life through interaction with a companion. Then there are X-ray pulsars, which work slightly differently. These are neutron stars and binary systems where matter from the companion star falls onto the neutron star's magnetic poles. As this material crashes into the surface at a significant fraction of light speed, it heats to tens of millions of degrees and emits intense X-rays. Because the material follows the magnetic field lines to the magnetic poles, the X-ray emission is concentrated there, and as the neutron star rotates, we see X-ray pulses. These systems are cosmic particle accelerators using gravity and magnetic fields to achieve energies we can barely approach with our most advanced technology on Earth. And then there are the truly exotic ones, magnetars, which we'll explore in detail later. But even among regular pulsars, there's tremendous diversity. Some pulsars emit giant radio bursts, sudden flares of radiation, thousands of times brighter than the normal pulses. Others show nulling behavior, where the pulses simply stop for seconds or minutes, then resume as if nothing happened. We still don't fully understand all these behaviors, which makes pulsars active areas of research even more than 50 years after their discovery. One of the most fascinating aspects of pulsars is their incredible precision. The best pulsars are more accurate timekeepers than the most precise atomic clocks we've built, millisecond pulsars. Those recycled neutron stars spinning hundreds of times per second maintain such regular periods that we can predict their pulses years in advance with accuracy measured in microseconds. This stability comes from the neutron star's enormous rotational inertia. An object with the mass of the Sun, concentrated in a 20-kilometer sphere, has so much angular momentum that external forces barely affect its rotation. It's like the ultimate flywheel storing rotational energy so effectively that it takes millions of years to slow down noticeably. Astronomers use this precision in remarkable ways. By carefully timing pulsar pulses over months and years, we can detect incredibly subtle effects. If a pulsar is in a binary system, its orbit causes slight variations in pulse arrival times due to the Doppler effect and gravitational time dilation. By analyzing these variations, we can determine the orbital parameters with extraordinary precision, measuring things like the eccentricity of the orbit, the masses of both objects, even the orientation of the orbital plane. This has led to some of the most stringent tests of general relativity ever performed, which we'll explore further when we discuss extreme physics around neutron stars. Have you ever wondered if we could use pulsars for navigation? The answer is yes, and space agencies are already developing this technology. Because pulsars are such stable beacons scattered throughout the galaxy, with known positions and periods, a spacecraft could potentially determine its position by observing multiple pulsars, much like GPS satellites work on Earth. NASA has tested this concept with the Sextant project, demonstrating autonomous navigation using X-ray pulsars. It's a beautiful example of how basic astronomical research can have practical applications. Objects born in the violent deaths of massive stars, studied out of pure scientific curiosity, might one day guide humanity's journey to the stars. But pulsars also teach us profound lessons about scientific discovery. Jocelyn Bell's detection of that first pulsar happened because she was paying attention, because she took seriously a signal that could easily have been dismissed as interference. How many other discoveries are waiting in data we've already collected but haven't noticed yet? And the Nobel Prize controversy reminds us that scientific credit is complicated, that the person who makes the key observation isn't always the one who receives recognition, and that we need to be vigilant about bias and fairness in how we acknowledge contributions to science. The discovery of pulsars transformed our understanding of neutron stars from theoretical abstractions into observable reality. They gave us a way to study these extreme objects, to measure their properties, to test our theories against actual data. But pulsars are just one way neutron stars reveal themselves. The physics of these objects goes far beyond rotation and radio beams. Neutron stars create some of the most extreme conditions in the universe, bending space-time, warping the flow of time itself, creating natural laboratories where Einstein's most mind-bending predictions become observable reality. The intersection of neutron stars and relativity opens up phenomena so strange they challenge our very conception of space and time. Imagine standing on the surface of a neutron star. Time itself would be flowing differently for you compared to the rest of the universe. A clock in your hand would tick noticeably slower than an identical clock orbiting safely far away. The fabric of space-time around you wouldn't just be curved. It would be twisted, dragged along by the star's rotation, like honey swirling around a spinning spoon. Light trying to escape the surface would struggle against gravity so intense that photons themselves are redshifted, losing energy in their desperate climb out of the gravitational well. This isn't science fiction. This is general relativity operating at full intensity. And neutron stars are the universe's natural laboratories, where Einstein's most radical predictions about the nature of space and time become not just measurable, but impossible to ignore. If you're enjoying this deep dive into the cosmos, where physics becomes beautifully strange, take a second to leave a like on this video. It truly helps this content reach others who share your fascination with the universe's mysteries. And don't forget to subscribe so you never miss our cosmic explorations. Albert Einstein published his theory of general relativity in 1915, fundamentally changing how we understand gravity. Newton had described gravity as a force acting at a distance between massive objects. Einstein reveals something far more profound. Gravity isn't a force at all, it's the curvature of space-time itself. Massive objects don't pull on other objects, they warp the geometry of the universe around them, and other objects follow the curved paths through this warped space-time. For most situations we encounter in daily life, Newton's simpler description works perfectly well. The difference between Newtonian and Einsteinian gravity only becomes significant in extreme conditions. Very strong gravitational fields, very high velocities, or very precise measurements over long periods. Neutron stars provide all three conditions, simultaneously making them ideal testing grounds for general relativity. Let's start with one of the most striking relativistic effects, gravitational time dilation. According to Einstein's theory, time flows more slowly in stronger gravitational fields. This isn't an illusion or a measurement error, it's a fundamental feature of how space-time works. Near a neutron star, this effect is dramatic. If you could somehow survive standing on a neutron star's surface and you had a twin in a spaceship orbiting safely far away, you would age noticeably slower than your twin. For every 3 seconds that pass for you on the surface, approximately 4 seconds would pass for your twin. Time itself is flowing about 30% slower at the surface of a typical neutron star, compared to locations far from its gravitational influence. Think about what this means. It's not that clocks run differently, it's that time genuinely passes at different rates depending on where you are in a gravitational field. We can actually measure this effect through observations of neutron stars. When a neutron star emits light from its surface, that light must climb out of the deep gravitational well to reach us. In doing so, the light loses energy, a phenomenon called gravitational redshift. The wavelengths get stretched out, shifted toward the red end of the spectrum. By measuring how much the light has been redshifted, astronomers can determine the strength of the gravitational field at the neutron star's surface, which in turn tells us about the star's mass and radius. This isn't just a theoretical curiosity. Gravitational redshift measurements from neutron stars have helped us test Einstein's predictions with remarkable precision, and they've also helped constrain those equations of state we discussed earlier, the theoretical models describing what neutron star matter actually is. But time dilation isn't the only relativistic effect neutron stars produce. There's an even stranger phenomenon called frame dragging, also known as the lens-Thirring effect, after the physicists who first predicted it. Imagine space-time as a fabric and a rotating massive object, as something spinning within that fabric. The spinning object doesn't just curve the fabric through its mass, it also drags the fabric along with its rotation, creating a kind of vortex in space-time itself. For most rotating objects, this effect is incredibly tiny, far too small to detect. But neutron stars, with their enormous mass and rapid rotation, create measurable frame dragging. What does frame dragging actually do? It affects the motion of anything near the neutron star. If you were in orbit around a spinning neutron star, your orbital plane would gradually precess, rotating slowly around the neutron star's rotation axis, not because of any force acting on you, but because space-time itself is being twisted. Your gyroscope's axis would also shift over time, pulled along by the rotating space-time. This sounds abstract, but astronomers have actually measured frame dragging around neutron stars by observing pulsars in binary systems. When a pulsar has a companion star, we can watch how the pulsar's beam sweeps across space. If the pulsar's rotation axis is precessing due to frame dragging, we'll see the beam angle change over time. These observations provide another crucial test of general relativity in extreme conditions. One of the most remarkable confirmations of Einstein's theory came from observing a binary pulsar system discovered in 1974 by Russell Hulse and Joseph Taylor. PSR B1913+16 consists of two neutron stars orbiting each other with a period of just under 8 hours. The system is extraordinary for several reasons. First, we can observe one of the neutron stars as a pulsar, giving us incredibly precise measurements of the orbital motion. Second, the orbit is quite elliptical, meaning the neutron stars get very close to each other at some points in their orbit. intensifying relativistic effects. Third, and most importantly, Einstein's theory predicts that this system should be radiating energy in the form of gravitational waves, ripples in space-time itself, propagating outward at the speed of light. Gravitational waves carry away energy and angular momentum from the system, which means the two neutron stars should be gradually spiraling closer together. Their orbital period should be decreasing very slowly but measurably. Hulse and Taylor, along with their colleagues, monitored this system for years, timing the pulsar signals with extraordinary precision, and they found exactly what Einstein's equations predicted. The orbital period was decreasing by about 76 millionths of a second per year, matching the theoretical calculation to better than 0.5% accuracy. This was the first indirect evidence that gravitational waves actually exist, a prediction Einstein made in 1916, but wasn't directly confirmed until a century later, with LIGO's detection of gravitational waves from merging black holes in 2015. The discovery earned Hulse and Taylor the Nobel Prize in Physics in 1993. What makes this observation so powerful is its precision. We're talking about measuring changes in an orbital period over years and comparing them to theoretical predictions involving some of the most complex mathematics in physics and finding agreement to a fraction of a percent. It's a stunning validation of general relativity, but it also tells us something profound about neutron stars. They're not just dense objects. They're dynamic systems that interact with space-time in ways we can observe and measure, providing natural experiments that would be impossible to recreate artificially. Another relativistic effect observable around neutron stars is called the Shapiro delay, named after physicist Erwin Shapiro, who predicted it in 1964. The basic idea is that light takes longer to travel through curved space-time than it would through flat space-time. If light from a distant source passes close to a massive object on its way to us, it experiences a time delay, arriving slightly later than it would if the massive object weren't there. For most astronomical situations, this delay is tiny, measured in microseconds or less, but neutron stars create strong enough gravitational fields that Shapiro delays become clearly measurable. The beautiful thing about binary pulsar systems is that we can use Shapiro delay to measure masses with incredible precision. When the pulsar's companion star passes between us and the pulsar's radio signals must travel through the curved space-time around the companion. The signals are delayed, and by measuring that delay, we can determine the companion's mass. Combined with other observations that give us the orbital parameters, we can separately measure the masses of both objects in the binary system. This is how we know, for instance, that the most massive neutron stars are around 2.0 to 2.1 times the mass of our Sun. These mass measurements are crucial for testing those theoretical equations of state, helping us understand what matter does at extreme densities. It's worth pausing to appreciate just how remarkable these measurements are. We're observing objects thousands of light years away, timing radio pulses from them with precision of microseconds, extracting information about their masses, orbital parameters, and the shape of space-time around them, and using those observations to test fundamental theories of physics. The fact that we can do this at all is a testament to both the precision of our instruments and the power of mathematical physics to describe reality. Now, let me tell you about one of my favorite relativistic effects around neutron stars, light bending. We know that gravity bends light. This was one of the first confirmations of general relativity during a solar eclipse in 1919, when astronomers observed stars appearing in slightly different positions because their light had been bent while passing near the sun. But around neutron stars, light bending is far more extreme. If you could look at a neutron star from the side, you wouldn't just see the half facing you, you'd also see part of the far side, because light from the back surface is bent around the star toward you. The star would look larger than its actual physical size, because you're seeing more than a hemisphere of its surface. This effect has practical applications for studying neutron stars. When hot spots on a neutron star's surface emit X-rays, the light bending means we can sometimes see hot spots, even when they're on the far side of the star from our perspective. This allows missions like NICER to map the distribution of temperature across a neutron star's surface, providing information about the star's magnetic field structure and helping us constrain its radius. The amount of light bending depends on the compactness of the neutron star, the ratio of its mass to its radius. So, by carefully modeling how we see X-ray emission as the star rotates, we can learn about its fundamental properties. There's a common misconception I want to address. Some people hear about these extreme relativistic effects and assume that neutron stars must be very close to becoming black holes. While it's true that neutron stars are the densest objects that aren't black holes, there's still a significant gap. A neutron star with 1.4 solar masses and a radius of about 12 kilometers has what's called an escape velocity of roughly half the speed of light. That's enormous, but it's not infinite light can still escape. A black hole's escape velocity, by definition, equals the speed of light at the event horizon. The difference might seem subtle, but it's fundamental. Neutron stars exist in a regime of strong gravity where relativistic effects are important, but space-time hasn't yet collapsed into a singularity. They're right at the edge, which is precisely what makes them so valuable for testing our theories. Another fascinating aspect of neutron stars and relativity involves what happens to matter falling onto them. In a process called accretion material from a companion star or the surrounding interstellar medium can fall toward a neutron star. As this matter spirals inward, it accelerates to tremendous speeds, approaching a significant fraction of light speed by the time it reaches the surface. Relativistic effects become crucial for understanding this process. The infalling matter doesn't just heat up through friction and compression, it also experiences time dilation and extreme gravitational redshift. The energy released when this material finally impacts the neutron star's surface is staggering, up to 10 to 20% of the matter's rest. Mass energy is converted to radiation. For comparison, nuclear fusion releases less than 1% of rest mass energy. This makes accreting neutron stars some of the most luminous objects in the universe for their size. The study of neutron stars has also revealed interesting limits on Einstein's theory. General relativity works extraordinarily well in all regimes. We've tested it from GPS satellites orbiting Earth to gravitational waves from merging black holes billions of light years away. But we know it can't be the complete story because it doesn't incorporate quantum mechanics, and at the very smallest scales and highest energies, quantum effects must become important. Neutron stars push both general relativity and quantum mechanics to their limits simultaneously. The intense gravity is a regime where Einstein's equations dominate, but the extreme density and the nature of neutron star matter involves quantum degeneracy pressure and possibly exotic quantum states of matter. Finding a unified theory that properly combines quantum mechanics and general relativity. A theory of quantum gravity remains one of the great challenges in theoretical physics. Can you imagine being able to see gravitational effects with your own eyes? Around a neutron star, you could. If you were in orbit around one with a good view, you'd see stars behind the neutron star appearing in distorted positions, stretched into arcs by gravitational lensing. You'd see the neutron star looking larger than its actual size due to light bending. If you looked at the Doppler shift of light coming from different parts of the rotating surface, you'd see one side blue shifted approaching you at a significant fraction of light speed, and the other side red shifted receding. The entire visual experience would be a constant reminder that you're in a region where space-time itself is dramatically curved and twisted. The insights we've gained from studying relativistic effects around neutron stars go far beyond academic interest. They've improved our understanding of gravity itself, validated Einstein's century-old predictions in regimes he never imagined, and revealed new ways that matter and energy interact with space-time. Every precise measurement of a neutron star's mass, Every observation of orbital decay in a binary system, every detection of frame dragging or Shapiro delay, adds to our confidence that general relativity correctly describes gravity even in the most extreme environments nature provides. But as extreme as standard neutron stars are, the universe has managed to create something even more bizarre: magnetars. Neutron stars with magnetic fields so powerful they defy comprehension objects, where the magnetic force dominates even over the intense gravity. These cosmic magnets represent yet another frontier of extreme physics, where our understanding is still incomplete and where each new observation brings surprises that challenge our theoretical models. On December 27, 2004, astronomers around the world witnessed something that should have been impossible. A burst of gamma rays and X-rays erupted from a neutron star 50,000 light-years away, so intense that it measurably affected Earth's ionosphere. For a tenth of a second, this object became brighter in gamma rays than the full moon is in visible light, despite being halfway across our galaxy. The wave of radiation was powerful enough to disrupt satellite operations and interfere with radio communications. This wasn't a supernova. It wasn't a black hole. It was a magnetar having what astronomers call a giant flare, and it revealed the existence of the most magnetically powerful objects in the known universe: neutron stars, with fields so strong they literally warp the quantum vacuum of space itself. If this journey into the universe's most extreme phenomena is resonating with you, I'd love your support. Hit that like button to help this video reach more cosmic explorers, and subscribe to stay connected as we continue unveiling the mysteries of the cosmos together. The magnetar that erupted in 2004 is known as SGR 180620, and its outburst fundamentally changed how we think about neutron stars. Before this event, astronomers knew magnetars existed, but their true power wasn't fully appreciated. The flare released more energy in 1/10 of a second than our sun produces in 100,000 years. To put that in perspective, imagine the total energy output of our sun, every photon of light and heat radiated in 100 millennia, compressed into a fraction of a second. The radiation was so intense that if SGR 180620 had been just 10 light-years away instead of 50,000, it would have caused a mass extinction on Earth, stripping away our ozone layer and bathing the surface in lethal radiation. We were protected only by the vast cosmic distance, but even at that, removed, the effects were measurable and startling. So, what exactly is a magnetar, and how can a magnetic field become powerful enough to cause such devastation? Magnetars are a subclass of neutron stars, but they are not distinguished by their mass or size. What makes them unique is their magnetic field strength. A typical neutron star has a magnetic field around 1 trillion times stronger than Earth's, which already seems impossibly powerful. But magnetars take this to another level entirely. Their magnetic fields reach quadrillion times Earth's strength, roughly 1,000 times stronger even than regular neutron stars. These are the strongest magnetic fields in the universe, period. Nothing we know of can generate more powerful magnetism. The numbers are so large they become abstract. So let me give you a sense of what this field strength actually means. The magnetic field of a magnetar at its surface is approximately 100 billion Tesla. To put that in context, the strongest continuous magnetic field ever produced in a laboratory on Earth is about 45 Tesla. And that requires enormous superconducting magnets and tremendous amounts of energy. The strongest pulsed magnetic field, lasting only fractions of a second before the equipment destroys itself, reaches maybe 1/200 Tesla. A magnetar's field is 100 million times stronger than that, sustained permanently across its entire surface. At this field strength, the magnetic force begins to dominate over even the electromagnetic forces that hold atoms together. The field is so intense that it affects the quantum vacuum itself, a concept that sounds like science fiction, but is actually predicted by quantum electrodynamics. In quantum field theory, what we think of as empty space isn't truly empty. It's filled with virtual particle-antiparticle pairs constantly popping into and out of existence. Under normal circumstances, these virtual particles exist for such infinitesimally short times that they have no observable effect. But in the presence of a magnetor's field, something remarkable happens. The magnetic field is strong enough to affect these virtual particles, causing a phenomenon called vacuum birefringence. The quantum vacuum becomes polarized, and light passing through it can actually be affected, changing its properties in ways that would never occur in normal space. This is physics at the absolute edge of our theoretical understanding, where quantum mechanics and classical electromagnetism meet in the most extreme conditions nature can provide. How do magnetars form? The current theory is that they're born from the collapse of particularly massive stellar cores that have rapid rotation and exceptionally strong magnetic fields to begin with. During the collapse, just as we discussed earlier, the magnetic field is amplified enormously. But in magnetars, this process is taken to an extreme, possibly through a dynamo mechanism in the first few seconds after formation, where convection currents in the proto-neutron star generate additional magnetic field strength. What emerges is a neutron star with a magnetic field so powerful that it dominates the object's behavior. Unlike regular pulsars, which are powered primarily by their rotation, magnetars are powered by their magnetic fields. As these fields evolve and decay over thousands of years, they release tremendous amounts of energy in the form of X-rays and gamma rays. The surface of a magnetar is a hellscape beyond imagination. The magnetic field is so strong that it creates enormous stresses in the neutron star's crust, the solid iron lattice we discussed earlier. These magnetic stresses can literally crack the crust, causing what astronomers call starquakes. Imagine earthquakes, but on a neutron star made of nuclear density matter. When a magnetar's crust fractures, it releases energy equivalent to thousands of large thermonuclear weapons. And this energy is channeled along the magnetic field lines, accelerating particles to enormous energies and producing the X-ray and gamma ray bursts we observe. The December 2004 giant flare from SGR 1806-20 was likely triggered by a massive starquake that violently reconfigured the magnetar's magnetic field. Let me tell you about another remarkable magnetar event that helped us understand these objects. On August 27, 1998, an object designated SGR 1900+14 produced a giant flare similar to, but somewhat less powerful than the 2004 event. What made this observation particularly valuable was that multiple spacecraft were monitoring different parts of the electromagnetic spectrum when it happened, allowing astronomers to piece together a comprehensive picture. The flare began with an initial spike lasting about 1/5 of a second, releasing as much energy as the sun produces in a week. This was followed by a pulsating tail of emission lasting several minutes, with the intensity oscillating with a period of 5.16 seconds, the magnetar's rotation period. By analyzing these oscillations, scientists determined that the magnetar's crust was literally ringing like a bell, vibrating in response to the violent starquake that triggered the flare. These oscillations provided direct information about the mechanical properties of neutron star matter, helping constrain those theoretical equations of state we keep coming back to. Now, here's something that might surprise you. Despite their fearsome power, magnetars are actually relatively rare. Out of the roughly 3,000 neutron stars, we've discovered only about 30 are confirmed magnetars. This rarity tells us something important about their formation. Not every neutron star becomes a magnetar, only those born under specific conditions that we're still working to fully understand. Moreover, magnetars are relatively short-lived on astronomical timescales. Their intense magnetic fields decay over roughly 10,000 years, after which they become dormant, indistinguishable from dead neutron stars that have cooled and stopped emitting. So, When we observe an active magnetar, we're seeing an object in a brief, spectacular phase of its existence, a cosmic fireworks display that will eventually fade to darkness. The effects of a magnetar's magnetic field extend far beyond the object itself. At a distance of 1,000 kilometers, roughly 600 miles, the magnetic field strength would be about 100,000 Tesla, still far beyond anything we can produce on Earth. At this distance, the field would be strong enough to disrupt atomic structure. The electron orbitals of atoms would be stretched into elongated shapes, making chemistry as we know it impossible. Complex molecules couldn't exist. Life, which depends on the stable configurations of organic molecules, would be utterly impossible anywhere near a magnetar. You wouldn't need to touch the surface to be destroyed. Simply being in the vicinity would be fatal in ways that go beyond radiation or heat. The magnetic field itself would rearrange the atoms in your body, tearing apart the molecular structures that make life possible. There's a common misconception about magnetars that I want to address. When people hear about objects with incredibly strong magnetic fields, they sometimes imagine them as cosmic magnets that would attract metallic objects from vast distances, like some kind of enormous refrigerator magnet. This isn't how magnetars work. Magnetic force, unlike gravity, falls off very rapidly with distance proportional to the inverse cube of distance for a dipole field. While a magnetar's field is unimaginably strong at its surface, by the time you're a few thousand kilometers away, it's already diminished significantly. More importantly, for a magnetic field to exert force on an object, that object must either be magnetized itself or contain moving electric charges. A spacecraft made of aluminum or plastic wouldn't be strongly affected. The real danger from a magnetar isn't its magnetic attraction, it's the intense radiation it produces, and the way its field affects the quantum properties of space itself. Another fascinating aspect of magnetars is how they challenge our understanding of neutron star structure. We mentioned earlier that neutron stars can spin at incredible rates, with the fastest known pulsar rotating 716 times per second. But magnetars spin much more slowly, typically once every few seconds. At first, this seems paradoxical. Both types of objects form through the same basic process of core collapse, which should conserve angular momentum. Why would magnetars rotate so much slower? The answer lies in their formation. During the birth of a magnetar, the enormous magnetic field interacts with the surrounding plasma and debris from the supernova. This interaction transfers angular momentum away from the protoneutron star, slowing its rotation. The stronger the magnetic field, the more efficiently this process works, which is why magnetars end up as relatively slow rotators, despite their violent origins. The study of magnetars also reveals something profound about magnetic field sustainability. According to electromagnetic theory, magnetic fields in conventional conductors decay relatively quickly through a process called ohmic dissipation. In ordinary materials, even superconductors' strong magnetic fields can't be sustained indefinitely without a power source to maintain them. Yet magnetar fields persist for thousands of years. How is this possible? The answer likely involves the unique properties of neutron star matter. In the outer core of a neutron star, matter exists in a superconducting state for protons and a superfluid state for neutrons. These exotic states of matter have essentially zero electrical resistance, allowing magnetic fields to persist without decaying. But the details are still not fully understood, and magnetars continue to provide crucial observational data that helps physicists refine their models of how matter behaves under these extreme conditions. What would it be like to observe a magnetar up close from a safe distance, of course? You'd be watching an object roughly the size of a city spinning once every few seconds, with a surface temperature of millions of degrees. The intense magnetic field would accelerate particles in the star's magnetosphere, creating beams of X-rays and gamma rays that sweep across space. Unlike regular pulsars with their steady, predictable pulses, magnetars are volatile. They produce frequent bursts of radiation. unpredictable flares that can occur multiple times per day or remain quiet for months. The magnetic field lines extending far from the star would trap and accelerate particles, creating a complex dynamic magnetosphere that constantly evolves and reorganizes. Occasionally, you might witness a giant flare, a cataclysmic release of magnetic energy that briefly makes the magnetar one of the brightest objects in the galaxy. The discovery and study of magnetars has forced astronomers to expand their understanding of what neutron stars can be. For decades after the discovery of pulsars, the focus was on rotation-powered neutron stars, objects that gradually spin down as they radiate away their rotational energy. Magnetars revealed that magnetic field decay could be an equally important or even dominant power source for some neutron stars. This has led to a more nuanced picture where neutron stars aren't a single category, but rather a diverse population with different properties and evolutionary paths. Some are rapid pulsars, some are magnetars, some are in binary systems, accreting matter from companions. And some have likely gone dormant, sitting invisibly in space as ultra-dense stellar corpses awaiting possible reactivation through some future interaction. Can you imagine the engineering challenge of detecting and studying these objects? Magnetars emit most of their energy as X-rays and gamma rays wavelengths that Earth's atmosphere fortunately blocks. This means we need space-based telescopes to observe them. Satellites like Swift Fermi and Integral constantly monitor the sky for magnetar outbursts, providing alerts within seconds when a flare is detected, so that other telescopes can quickly observe the event. These observations have revealed that magnetars are more common than initially thought, and that many neutron stars previously classified as regular pulsars might actually be magnetars with weaker fields or in quieter phases of activity. The boundary between magnetars and regular neutron stars is becoming increasingly blurred as our observations improve. Magnetars also play a crucial role in understanding one of astronomy's recent mysteries, fast radio bursts. These are brief, intense pulses of radio waves from the distant galaxies lasting just milliseconds, but releasing as much energy as the sun produces in days. For years, their origin was unknown. But in April 2020, astronomers detected a fast radio burst from a magnetar in our own galaxy, SGR 1935 Plo-2154. This was the smoking gun linking at least some fast radio bursts to magnetars, though the exact mechanism remains under investigation. It appears that magnetar flares can somehow produce coherent radio emission, possibly through interactions between the magnetar's magnetosphere and surrounding plasma. This discovery has opened up an entirely new area of research connecting the extreme physics of magnetars to phenomena occurring in distant galaxies. As we reflect on these cosmic dynamos, magnetars remind us that the universe continually surprises us with phenomena more extreme than our theories initially predicted. They operate at the intersection of multiple physical extremes, incredible density, intense gravity, rapid rotation, and now magnetic fields at the absolute theoretical maximum that physics permits. But magnetars, dramatic as they are, don't exist in isolation. Many neutron stars, magnetars or not, have companion objects creating binary systems, where two stellar remnants orbit each other in an intricate cosmic dance. These partnerships lead to some of the most energetic and fascinating phenomena in the universe scenarios, where neutron stars become vampires, stealing matter from their companions in a process that illuminates the darkness of space with brilliant X-rays. Picture two stellar corpses locked in a gravitational embrace, orbiting each other so closely they complete a full circuit in just hours. One is a neutron star, the compressed core of a dead giant. The other might be a white dwarf, another neutron star, or perhaps a normal star that found itself trapped in this deadly partnership. The neutron star's gravity is so intense, it literally tears matter away from its companion, pulling streams of gas that spiral inward, heating to millions of degrees. and emitting brilliant X-rays that can be detected across the galaxy. This isn't a peaceful coexistence. It's cosmic vampirism, a slow-motion destruction, where one object feeds on another, and the process reveals physics so extreme it challenges everything we thought we knew about how matter and energy behave in the universe. If you're captivated by these cosmic relationships and the extreme physics they reveal, please take a moment to like this video. Your engagement genuinely helps these stories reach more people who share your curiosity about the cosmos. And if you're not yet subscribed, join our community of space enthusiasts exploring the universe together. Binary star systems are actually quite common in the universe. Roughly half of all stars exist in gravitationally bound pairs, or groups rather than in isolation, like our Sun. Most of these binaries are unremarkable to normal stars orbiting their common center of mass, maintaining a stable relationship for billions of years. But when one or both stars in a binary system dies and becomes a compact object, a white dwarf, neutron, star, or black hole, the dynamics change dramatically. Suddenly you have an object with extreme gravity and close proximity to a companion. And this creates conditions for some of the most energetic and bizarre phenomena we observe in astronomy. Let's start with one of the most fascinating types of binary system, black widow pulsars. The name comes from the black widow spider, where the female sometimes consumes the male after mating. In astronomical terms, a black widow pulsar is a millisecond pulsar, a rapidly rotating neutron star paired with a very low-mass companion star. The pulsar emits intense radiation and a powerful wind of high-energy particles that literally evaporates its companion. Over millions of years, the companion star is being destroyed, its outer layers stripped away by the pulsar's relentless assault. Eventually, the companion will be completely consumed, leaving behind only the pulsar alone once again, but now spinning at incredible speeds, thanks to the angular momentum it stole from its former partner. The first Black Widow pulsar was discovered in 1988, designated PSR B1957+20. This system perfectly illustrates the destructive dynamic. The pulsar spins 622 times per second, one of the fastest rotation rates known. Its companion is a brown dwarf, an object too small to sustain nuclear fusion, with only about 2% the mass of our Sun. The orbital period is just 9.2 hours, meaning these two objects are separated by only about 2 million kilometers closer than the Sun is to its innermost planet Mercury. The pulsar's radiation is so intense that it heats the side of the companion, facing it to about 6,500 degrees Celsius, nearly as hot as the Sun's surface. Material is being blown off the companion at a rate of roughly 100 billion tons per year. This sounds like a lot, but the companion is so small that at this rate it will take another 100 million years before it's completely destroyed. What makes Black Widow systems particularly valuable for science is that the evaporating companion creates a cloud of material around the system. As the pulsar's radio beams pass through this cloud, they're affected in ways that allow astronomers to probe the system's properties with remarkable precision. By analyzing how the radio signals are delayed or scattered, we can map the structure of the evaporating material, determine the orbital parameters with extraordinary accuracy, and even measure the masses of both objects. Some of the most precise neutron star mass measurements we have come from Black Widow systems. Now, let's discuss a different type of binary interaction, accretion-powered X-ray sources. These systems consist of a neutron star with a companion that's still a normal living star. The neutron star's gravity is so strong that it pulls matter away from the companion's outer layers, particularly if the companion has evolved into a red giant and expanded to the point where its outer atmosphere extends toward the neutron star. This stolen matter doesn't fall directly onto the neutron star. Because both objects are orbiting their common center of mass, the infalling material has angular momentum, causing it to spiral inward and form what's called an accretion disk. Accretion disks are one of the most common structures in high-energy astrophysics, appearing around white dwarfs, neutron stars, and black holes. As matter in the disk spirals inward, friction between adjacent layers of gas converts gravitational potential energy into heat. The inner parts of the disk, closest to the neutron star, reach temperatures of millions of degrees hot enough to emit X-rays. In fact, these accreting neutron star systems are among the brightest X-ray sources in the sky, often outshining entire galaxies, despite being just single binary star systems. The X-ray emission fluctuates as blobs of material fall onto the neutron star, and by studying these fluctuations, astronomers can learn about the dynamics of accretion and the properties of the neutron star itself. One particularly well-studied example is Hercules X1, discovered in 1972 by the Uhuru satellite, the first spacecraft specifically designed to observe cosmic X-ray sources. Hercules X1 consists of a neutron star, accreting matter, from a companion star called HZ Hercules. The system shows periodic variations on multiple time scales that tell a rich story about its structure. Every 1.24 seconds, we see X-ray pulses as the neutron star rotates and its magnetic poles sweep past our line of sight. Every 7 days, the system shows a longer period variation, as the neutron star's rotation axis precesses changing the angle at which we view its emission. And every 1.7 days, the X-rays are eclipsed entirely, as the companion star passes in front of the neutron star from our perspective. By carefully analyzing all these periodicities, astronomers have been able to reconstruct the three-dimensional geometry of the system, determine that the neutron star has a mass about 1.5 times that of the Sun, and even detect effects of general relativity in the system's orbital dynamics. The accretion process itself is fascinating. When material from the accretion disk finally reaches the neutron star's magnetosphere, the strong magnetic field channels it toward the magnetic poles. This creates hot spots at the magnetic poles where the infalling material crashes into the neutron star's surface at a significant fraction of light speed. The kinetic energy of this impact is converted into thermal energy and radiation. Up to 10 to 20% of the infalling matter's rest mass energy can be released as radiation, making accreting neutron stars incredibly efficient power sources. For comparison, nuclear fusion releases less than 1% of rest mass energy and chemical reactions. Like burning fossil fuels, release only about 1/billionth of rest mass energy. Only matter falling into black holes can be more efficient, potentially converting up to 40% of rest mass energy into radiation under ideal conditions. Binary systems also play a crucial role in something called pulsar recycling. Remember that normal pulsars gradually spin down over millions of years, losing rotational energy as they emit radiation. Eventually, they slow down enough that they can no longer generate the conditions needed for radio emission, and they become invisible to our radio telescopes. But if a dead pulsar happens to be in a binary system, it can be brought back to life. When the companion star evolves and expands, it can begin transferring matter to the neutron star. This infalling matter carries angular momentum, and over millions of years, it spins the neutron star back up to rapid rotation. The neutron star is recycled, transformed from a dead pulsar into a millisecond pulsar, spinning hundreds of times per second. This process explains why we see old neutron stars with such rapid rotation rates. They've been spun up by accretion rather than retaining their birth spin from the original supernova. The most extreme binary systems are those containing two neutron stars. These double neutron star systems are relatively rare because they require two massive stars in a binary to both explode as supernovae without the system being disrupted. When the first star explodes, the sudden loss of mass can potentially unbind the system, sending both objects flying apart. For the system to remain bound, the supernova must be relatively symmetric. and the stars must be in the right orbital configuration. Despite these constraints, we've discovered several dozen double neutron star systems, and they're scientifically invaluable because they provide the cleanest tests of general relativity and the most precise measurements of neutron star masses. The double pulsar system, PSR J07373039, is particularly remarkable. Discovered in 2003, this system contains two neutron stars, both of which we can observe as pulsars. One spins 44 times per second, the other 2.8 times per second. They orbit each other every 2.4 hours, separated by just about 800,000 kilometers, less than 3 times the distance from Earth to the Moon. The system is tilted such that we see it nearly edge-on, which means that once per orbit, the radio beam from one pulsar passes through the magnetosphere of the other. This creates a unique opportunity to probe one pulsar's magnetosphere using the other pulsar as a lighthouse. The observations have revealed details about the structure and dynamics of pulsar magnetospheres that would be impossible to obtain any other way. What happens in these close binary systems as they evolve? Einstein's general relativity predicts that any accelerating mass produces gravitational waves, ripples in space-time itself. For most astronomical objects, gravitational wave emission is negligibly weak, but in close binary systems with compact objects, the effect becomes significant. The two neutron stars orbit each other so quickly and with such strong gravitational fields that they emit substantial gravitational wave radiation. These waves carry away energy and angular momentum from the system, causing the orbit to gradually shrink. The two neutron stars spiral slowly closer together in a process that will eventually lead to a catastrophic merger. For most double neutron star systems, this in-spiral takes hundreds of millions or even billions of years. But the effect is real and measurable. The Hulse-Taylor binary pulsar, which we mentioned earlier, provided the first evidence of this orbital decay. By timing the pulsar signals over decades, astronomers observed that the orbital period was decreasing by exactly the amount predicted by general relativity's equations for gravitational wave emission. This indirect detection of gravitational waves earned Hulse and Taylor the Nobel Prize and confirmed that Einstein's most exotic prediction was correct. As two neutron stars spiral together, their orbital period decreases and they move faster and faster. In the final seconds before merger, they orbit each other hundreds of times per second, moving at a significant fraction of light speed. The gravitational wave emission becomes extremely strong, and when the stars finally collide, the result is one of the most energetic events in the universe, a kilonova. This is distinct from a supernova. Where a supernova is powered by the collapse of a massive star's core, a kilonova is powered by the collision of two stellar corpses, and the energy release is comparable. For a brief time, a kilonova can outshine an entire galaxy of billions of stars. Have you ever wondered where the gold in your jewelry comes from? The answer involves binary neutron stars. During a kilonova, the extreme temperatures, densities, and neutron-rich environment create ideal conditions for a process called rapid neutron capture, or the R process. Atomic nuclei are bombarded with so many neutrons so quickly that they build up into the heaviest elements in the periodic table: gold, platinum, uranium, thorium, and many others. These elements are scattered into space by the explosion, mixing with interstellar gas clouds that will eventually form new stars and planets. Earth's supply of gold and all the heavy elements beyond iron were forged in kilonovae billions of years ago, long before our solar system formed. You're literally wearing the remnants of neutron star collisions. Binary systems also reveal important insights into stellar evolution. The mere existence of double neutron star systems tells us that some supernovae are relatively symmetric and don't impart huge kicks to the stellar remnant. If all supernovae gave the neutron star a large velocity in a random direction, no binary systems could survive. The fact that we see binaries means nature has found ways to produce supernovae that don't necessarily destroy the gravitational bond between companion stars. Understanding how this works helps refine our models of how massive stars die and what determines whether a particular supernova will be symmetric or asymmetric. There's a common misconception about binary systems that's worth addressing. People sometimes imagine that the two objects are pulling on each other, actively fighting against separation, like two wrestlers locked in combat. But gravitationally bound systems aren't fighting, they're dancing. Both objects are falling freely through space-time, following geodesics, the natural paths determined by the curved space-time geometry created by their combined mass. It's only when additional forces like tidal effects or radiation extract energy from the orbit that the system's configuration changes. Without such energy loss, a binary system could orbit forever in a stable equilibrium, each object perfectly balanced between its orbital momentum and the gravitational attraction of the system. The study of binary systems has practical implications beyond pure science. X-ray binary systems are so bright, they can be observed in distant galaxies, providing unique probes of stellar populations in environments very different from our Milky Way. By cataloging X-ray binaries in other galaxies, astronomers can learn about the rate of massive star formation, the fraction of stars born in binaries, and even the history of star formation over cosmic time. These systems are cosmic beacons announcing themselves with their brilliant high-energy emission and providing windows into physical processes we can't study any other way. As we contemplate these cosmic partnerships, these dances of death between stellar remnants, we're reminded that the universe is fundamentally interactive. Objects don't exist in isolation. They influence each other through gravity, they exchange matter and energy, they spiral together, and sometimes collide in spectacular fashion. Binary neutron star systems represent some of the most extreme versions of these interactions, and they lead directly to one of the most exciting developments in modern astronomy. Because when two neutron stars finally merge after spiraling together for eons, they don't just produce a visual spectacle. They create ripples in the very fabric of space-time gravitational waves that wash across the universe at the speed of light, carrying information about the collision encoded in the pattern of space-time distortion. The detection of these waves has opened an entirely new window on the cosmos, allowing us to observe the universe not through light, but through gravity itself. At 8:41 a.m. Eastern Time on August 17, 2017, two detectors separated by 3,000 kilometers simultaneously recorded a signal that had been traveling through space for 130 million years. It wasn't light. It wasn't radio waves. It was a ripple in space-time itself, a gravitational wave produced by two neutron stars spiraling into each other at nearly the speed of light before colliding in a catastrophic merger. For exactly 100 seconds, instruments on Earth tracked this cosmic collision in real-time, watching as the orbital frequency increased from dozens to hundreds of cycles per second before cutting off abruptly at the moment of impact. This wasn't just another astronomical observation. It was the birth of an entirely new way of experiencing the universe, one where we listen to gravity itself, speaking to us across the cosmic void. If this journey into humanity's newest window on the universe is inspiring, you please show your support with a like. It helps this content reach more curious minds eager to understand the cosmos. And subscribe to join us as we continue exploring the frontiers of space and time together. Gravitational waves are perhaps Einstein's most audacious prediction. When he completed his general theory of relativity in 1915, the equations contained a subtle implication: accelerating masses should create disturbances in space-time that propagate outward at light speed, much like how accelerating electric charges create electromagnetic waves. But Einstein himself doubted we'd ever detect them because the effects are extraordinarily weak. Even the most violent astronomical events produce gravitational waves that stretch and compress space by less than 1 part in a billion trillion. To put that in perspective, LIGO, the Laser Interferometer Gravitational Wave Observatory, can detect changes in the 4-kilometer distance between its mirrors smaller than 1/10,000th the diameter of a proton. It's like measuring the distance from Earth to the nearest star and being sensitive to changes smaller than the width of a human hair. The technical challenge of detecting gravitational waves is almost incomprehensible. Every source of noise, from passing trucks to distant earthquakes to quantum fluctuations in the laser light itself, threatens to overwhelm the signal. LIGO's detectors are marvels of engineering, using mirrors suspended as pendulums to isolate them from ground vibrations operating in ultra-high vacuum, to eliminate air currents employing laser systems stabilized to an absurd degree. 2 detectors were built, one in Hanford, Washington, and another in Livingston, Louisiana, specifically so that real gravitational wave signals could be distinguished from local disturbances by requiring simultaneous detections at both sites. The construction of LIGO represented a gamble by the scientific community, spending hundreds of millions of dollars on an experiment that might never detect anything. But the gamble paid off spectacularly. On September 14, 2015, just days after the advanced LIGO detectors began their first observing run, they detected gravitational waves from 2 merging black holes, each about 30 times the mass of the Sun, located 1.3 billion light-years away. This first detection earned the Nobel Prize in Physics in 2017 and confirmed that gravitational waves exist exactly as Einstein predicted. But the detection on August 17, 2017 was different and in many ways even more significant. This signal came from merging neutron stars, and unlike black hole mergers, which are invisible to traditional telescopes, this event produced a brilliant optical and gamma-ray counterpart that could be observed across the electromagnetic spectrum. It became the most intensely studied astronomical event in history, observed by more than 70 telescopes on the ground and in space across wavelengths, from radio to gamma rays. Let me walk you through what happened during those 100 seconds of gravitational wave signal. The 2 neutron stars, each about 1.4 times the mass of the Sun and roughly 12 kilometers in diameter, started the detection period orbiting each other about 400 kilometers apart, completing one orbit every few seconds. As they orbited, they emitted gravitational waves, losing energy and spiraling closer together. The gravitational wave frequency, which equals twice the orbital frequency, started at about 24 Hz in the range of human hearing. As the neutron stars spiraled inward, they moved faster and faster, and the gravitational wave frequency increased. By analyzing this frequency, evolution scientists could extract enormous amounts of information. The rate at which the frequency increased told them the combined mass of the 2 neutron stars. The precise waveform shape revealed information about their individual masses, their spins, and even their internal structure through something called tidal deformability. What is tidal deformability? As 2 neutron stars get very close together, their mutual gravitational fields begin to distort each other, pulling each object into a slightly ellipsoidal shape rather than a perfect sphere. How much a neutron star deforms under this tidal stress depends on its internal structure, specifically on that equation of state we keep mentioning. A softer equation of state, where matter is more compressible, means the neutron star deforms more easily. A stiffer equation of state means it resists deformation. The gravitational waves carry information about this tidal deformation, encoded in subtle features of the waveform. By carefully analyzing the GW1-0817 signal, as it's officially designated, scientists were able to place constraints on neutron star equations of state, ruling out some theoretical models and favoring others. This is remarkable. We use gravitational waves from a collision 130 million light-years away to probe the properties of matter at nuclear densities, something we cannot achieve in any laboratory on Earth. But the gravitational wave signal was only the beginning of the story. About 1.7 seconds after the gravitational waves arrived, the Fermi Gamma Ray Space Telescope detected a short gamma-ray burst from the same region of sky. This confirmed that at least some short gamma-ray bursts, mysterious flashes of gamma rays, lasting less than 2 seconds, are produced by neutron star mergers. The gamma-ray detection also provided crucial timing information, allowing astronomers to quickly narrow down the location in the sky where the merger occurred. Within hours, optical telescopes around the world were scanning that region, and they found a new point of light in the galaxy NGC 4993, located in the constellation Hydra, about 130 million light-years from Earth. This optical counterpart was a kilonova, the light produced when neutron-rich material ejected from the merger undergoes radioactive decay. The early observations showed blue light, which over the following days shifted to red and infrared as the expanding debris cooled. By observing the kilonova spectrum, astronomers detected the signatures of heavy elements like gold platinum and rare earth elements being synthesized in real time. This was the definitive confirmation that neutron star mergers are responsible for producing most of the universe's supply of elements heavier than iron. The R-process nucleosynthesis we discussed earlier wasn't just theoretical, it was happening right there in the expanding fireball, and we were watching it with telescopes across the electromagnetic spectrum. The multi-messenger nature of this observation cannot be overstated. For essentially all of human history, astronomy meant looking at light from celestial objects. Over the 20th century, we expanded our view to include radio waves, X-rays, gamma rays, and other forms of electromagnetic radiation. But the GW170817 event combined gravitational waves, electromagnetic radiation across the spectrum, and likely neutrinos, though those weren't definitively detected. This is multi-messenger astronomy, observing a single event through multiple fundamental carriers of information. It's like the difference between watching a silent movie and watching one with sound, color, and surround audio. Each messenger provides different information, and combining them creates a far richer understanding than any single type of observation could provide. What did we learn from this extraordinary event? The scientific output has been staggering. Over 4,000 scientific papers have been published, analyzing various aspects of GW170817. Here are just some of the insights. We confirmed that gravitational waves travel at the speed of light to within 1 part in a quadrillion, ruling out many alternative theories of gravity. We placed the best constraints yet on neutron star equations of state. We confirmed the origin of short gamma-ray bursts. We directly observed R-process nucleosynthesis and confirmed that neutron star mergers produce most of the universe's gold and platinum. We obtained an independent measurement of the Hubble constant, the expansion rate of the universe, using gravitational waves as a standard siren. This method is completely independent of the traditional cosmic distance ladder and helps address a current controversy in cosmology about why different measurement methods give slightly different values for the Hubble constant. The energy released in the GW170817 merger is almost incomprehensible. In the final second before the neutron stars collided, they emitted gravitational wave power, equivalent to converting about 5% of the sun's mass into pure energy. That's more power than all the stars in the observable universe combined, radiated as gravitational waves in 1 second. And this happened 130 million years ago. The ripples in space-time have been traveling across the universe all that time, spreading out and weakening until they finally reached Earth in August 2017 and stretched our detectors by a distance smaller than an atomic nucleus. Can you imagine what the view would be like if you could somehow safely observe a neutron star merger up close? In the final minutes before collision, you'd see two city-sized spheres orbiting each other hundreds of times per second, moving at a significant fraction of light speed. The intense gravity would create dramatic light-bending effects, showing you multiple distorted images of each neutron star. As they touched and began to merge, tidal forces would tear matter from both objects, creating a massive accretion disk of neutron-rich material surrounding the merged object. Some of this material would be ejected at high speed, beginning its radioactive decay and glowing with blue light that would quickly shift through the spectrum. At the center, depending on the total mass, either a hypermassive neutron star or a black hole would form. If a hypermassive neutron star formed, it would be unstable, supported temporarily by rapid rotation, but doomed to collapse into a black hole within seconds or hours. Throughout this entire process, jets of particles accelerated to near light speed might emerge along the rotation axis, producing the gamma-ray burst if Earth happened to lie along their path. The detection of GW170817 also revealed something surprising about neutron star maximum masses. Before the merger, there were two neutron stars each around 1.4 solar masses. After the merger, there was briefly a single object with a combined mass of about 2.8 solar masses. For this merged object to survive even temporarily as a neutron star, rather than immediately collapsing to a black hole, it means neutron stars can support masses higher than what we typically observe. The maximum mass of a non-rotating neutron star is probably around 2.0 to 2.2 solar masses, but rapid rotation can temporarily support higher masses. This hypermassive neutron star phase might last anywhere from seconds to hours before the rotation slows enough that collapse becomes inevitable. One of the most common misconceptions about gravitational waves is that they're like sound waves traveling through space. While gravitational waves do compress and stretch space in a rhythmic pattern that can be converted to audio frequencies for human listening, the analogy breaks down quickly. Sound waves are vibrations of matter, molecules of air or water or solid material oscillating back and forth. Gravitational waves are oscillations of space-time itself, the very fabric of the universe rippling like waves on a pond. No medium is required. In fact, gravitational waves propagate just fine through the vacuum of space where sound cannot travel at all. When scientists listen to gravitational waves by converting them to audio, they are creating a representation to help our human senses perceive what's happening, not because gravitational waves are actually sound. The field of gravitational wave astronomy is still in its infancy. LIGO has been joined by Virgo, in Italy Cagra, in Japan, and soon by LIGO India. Each additional detector improves our ability to locate gravitational wave sources on the sky. More detectors also means better sensitivity to different gravitational wave polarizations, and more confidence in detecting real signals versus noise. Future detectors, like the proposed Einstein telescope in Europe or Cosmic Explorer in the United States, will be even more sensitive, able to detect neutron star mergers throughout the entire observable universe. Space-based detectors like LISA, the Laser Interferometer Space Antenna, will open up entirely new frequency ranges, detecting gravitational waves from supermassive black hole mergers and extreme mass ratio in spirals, where small compact objects spiral into massive black holes. Every detection teaches us something new. Some neutron star mergers produce bright kilonovae, others are fainter. Some create clear gamma-ray bursts, others don't. The gravitational wave signals vary depending on the masses, spins, and internal structure of the merging objects. By building up a catalog of observations, astronomers are creating a census of the neutron star population, understanding the distribution of masses, spin rates, and orbital configurations. This tells us about the lives and deaths of massive stars, about supernova explosion mechanisms, about the formation of compact binary systems. It's a new kind of cosmic archaeology, reading the history of stellar evolution. written in the gravitational wave signals from neutron star mergers. The fact that we can observe gravitational waves at all is a testament to human ingenuity and persistence. Einstein published his prediction in 1916. It took 99 years before we had the technology to detect them directly. Generations of physicists and engineers worked on this problem, developing ever more sensitive instruments, fighting noise sources, perfecting analysis techniques. The payoff has been extraordinary, a completely new way of observing the universe that complements and extends what we can learn from light. We're no longer just watching the universe, we're listening to it through the vibrations of space-time itself. As revolutionary as gravitational wave astronomy has been, each new discovery also highlights how much we still don't understand. The exact process by which neutron star mergers produce gamma-ray bursts remains unclear. The fate of the merged object, whether it becomes a black hole immediately or survives as a hypermassive neutron star, depends sensitively on properties we're still working to constrain. And the fundamental question underlying all of this, what exactly is neutron star matter made of in its core, remains tantalizingly just beyond our current ability to answer definitively. Each gravitational wave detection provides new clues narrowing the range of possibilities, but the complete answer continues to elude us, drawing us deeper into the mysteries at the heart of these extraordinary objects. We've observed neutron stars from every conceivable angle. We've measured their masses with exquisite precision, timed their pulses to microsecond accuracy, detected their gravitational waves, analyzed their X-ray emissions, and mapped their surface temperatures. Yet, despite all this observational prowess, there's one fundamental question we still cannot answer with certainty. What exactly exists at the very center of a neutron star? Is it a sea of neutrons pressed together into nuclear density? Is it a soup of quarks liberated from their usual confinement? Is it something even more exotic, particles we've never seen in our laboratories existing, only in these extreme natural laboratories scattered across the cosmos? The truth is, we don't know. And this uncertainty represents one of the most tantalizing frontiers in modern physics. If this exploration of the universe's deepest mysteries is captivating you, please take a moment to like this video. Every like helps us share these cosmic wonders with more curious minds. And subscribe to continue this journey through space and time together. The question of what's inside a neutron star isn't just academic curiosity. It touches on fundamental issues in nuclear physics, particle physics, and the nature of matter itself. To understand why this remains mysterious, we need to appreciate what physicists call the equation of state, a mathematical relationship that describes how matter behaves under different conditions of temperature, density, and pressure. For familiar materials like water or iron, we know the equation of state extremely well from centuries of experiments. We know exactly how water behaves when compressed or heated. But for matter at densities exceeding that of atomic nuclei, we're in largely uncharted territory. We can't create such conditions in laboratories, at least not in stable, controllable ways. The only place this matter exists is inside neutron stars, and we can't exactly cut one open to look inside. Theoretical physicists have developed numerous competing models for the neutron star equation of state, each based on different assumptions about how nuclear forces operate at extreme densities. Some models predict relatively soft equations of state, where matter is more compressible, yielding smaller neutron stars for a given mass. Others predict stiff equations of state, where matter resists compression more strongly, producing larger neutron stars. The key is that these differences in the equation of state lead to observable consequences. A soft equation of state implies smaller maximum masses for neutron stars, perhaps around 1.9 solar masses. A stiff equation of state allows more massive neutron stars, potentially up to 2.5 solar masses or beyond. By measuring actual neutron star masses and radii, we can rule out equations of state that don't match observations. This is where missions like NICER become crucial. The Neutron Star Interior Composition Explorer, mounted on the International Space Station since 2017, is specifically designed to measure neutron star radii with unprecedented precision. The technique is ingenious. NICER observes X-ray pulsars, watching how X-ray bright spots on the star's surface come into and out of view as the star rotates. But because gravity bends light around the neutron star, we can actually see more than half the surface at any given time. The exact pattern of X-ray brightness as the star rotates depends on the star's radius, its mass, and the amount of light bending. By carefully modeling these effects and fitting them to observations, scientists can determine the radius to within about 1 kilometer, an incredible achievement considering these objects are thousands of light years away and only 20 kilometers across. The first results from NICER, published in 2019 and 2021, focused on 2 pulsars, PSR J0030+0451 and PSR J0740+620. The measurements revealed radii of about 13 kilometers for J0030+0451, which has a mass of 1.4 solar masses, and about 13 to 14 kilometers for J0740+6CR2, which is more massive at 2.08 solar masses. These measurements immediately ruled out some of the softest equations of state, those that predicted substantially smaller radii. But they also showed that we're not dealing with the stiffest possible equations of state either. The data point towards something intermediate matter that's neither maximally resistant to compression nor easily compressible. This is valuable information, but it's still not enough to tell us definitively what's happening in the core. Let's dive deeper into the competing theories about neutron star cores. The simplest model assumes that neutron stars are indeed made mostly of neutrons, with a small percentage of protons and electrons to maintain electrical neutrality. In this picture, the core is essentially a superfluid of neutrons, a quantum state where the particles flow without any viscosity, and a superconductor of protons where electrical resistance drops to absolute zero. These exotic quantum states of matter have been observed in laboratory systems at very low temperatures, but in neutron stars, they occur despite temperatures of millions of degrees, because the density is so extreme that quantum effects dominate over thermal effects. This neutron-proton-electron model is the baseline, the simplest possibility consistent with basic nuclear physics. But there are good reasons to think the core might be more exotic. As density increases beyond a certain threshold, roughly 2 to 3 times nuclear density, it may become energetically favorable to convert some neutrons into heavier particles called hyperons. Hyperons are similar to neutrons and protons, but contain strange quarks in addition to the up and down quarks found in normal matter. The lightest hyperons, the lambda and sigma particles, have masses only slightly greater than neutrons. At high densities, the Fermi energy of neutrons, essentially the energy cost of adding one more neutron to an already crowded system, becomes so large that converting some neutrons into hyperons actually reduces the total energy, even though hyperons are individually heavier. If this hyperon conversion occurs, neutron star cores would contain a mixture of neutrons, protons, hyperons, and electrons, creating what physicists call hyperonic matter. The hyperon puzzle is one of the major unsolved problems in neutron star physics. Calculations suggest that if hyperons appear at densities found in neutron star cores, they soften the equation of state significantly. This is because hyperons provide an additional degree of freedom, another way for the system to respond to compression, which makes the matter more compressible overall. The problem is that a soft equation of state from hyperons predicts maximum neutron star masses around 1.5 to 1.6 solar masses. But we've observed neutron stars with masses exceeding 2.0 solar masses, with the current record holder, PSR J0740+620, at 2.08 solar masses, and another PSR J09520607 potentially reaching 2.35 solar masses. These massive neutron stars seem incompatible with substantial hyperon populations in the core. Either our calculations of when hyperons appear are wrong, or there's some additional stiffening mechanism we don't understand, or perhaps hyperons simply don't appear in neutron star cores despite theoretical expectations. Then there's the possibility that the core contains deconfined quark matter. In normal atomic nuclei, quarks are always confined inside protons and neutrons by the strong nuclear force. You can't isolate a single quark. Trying to pull quarks apart just creates more quark-antiquark pairs. But at sufficiently high densities, quantum chromodynamics, the theory describing how quarks interact, predicts a phase transition to deconfined quark matter, where quarks are no longer bound inside individual particles, but instead form a continuous fluid. This quark matter would likely be in a color superconducting state, a quantum phase where quarks pair up in specific ways that reduce the system's energy. If neutron star cores reach densities sufficient for this phase transition, the innermost region might be a quark matter core, surrounded by a shell of hadronic matter, neutrons, protons, and possibly hyperons. One particularly exotic possibility is that the entire neutron star might be made of strange quark matter, creating what's called a strange star. Strange quarks are heavier than up and down quarks, and normally they're unstable, decaying into lighter quarks in a fraction of a second. But there's a hypothesis. The strange matter hypothesis that suggests absolutely stable strange quark matter could exist if the mixture of up-down and strange quarks is properly balanced. If this hypothesis is correct, strange quark matter might actually be the true ground state of matter, more stable than iron nuclei or anything else. Ordinary atomic nuclei would be metastable only because converting them into strange matter requires overcoming a large energy barrier. But in the extreme conditions during neutron star formation, this barrier might be overcome, converting the entire object into strange quark matter. Strange stars would look similar to neutron stars from outside, but have radically different internal structure and properties. How can we distinguish between these possibilities? The key is making precise measurements that depend sensitively on the equation of state. Mass and radius measurements are crucial because different equations of state predict different mass-radius relationships. Observations of tidal deformability during neutron-star mergers, like we obtained from Janzevelin 7081, also constrain the equation of state because softer matter is more easily deformed by tidal forces. Another promising avenue involves studying neutron star cooling. Different core compositions cool at different rates because they have different neutrino emission mechanisms. By measuring the surface temperature of neutron stars of known age, we can infer something about their internal composition and test cooling models. There's also the Tolman-Oppenheimer-Volkoff limit the maximum mass a neutron star can have before it must collapse into a black hole. This limit isn't a single number, but depends on the equation of state. For typical equations of state, the TOV limit falls somewhere between 2.0 and 2.5 solar masses. The exact value depends on whether the core is purely hadronic, contains hyperons, or transitions to quark matter. By finding the most massive neutron stars we can observe, we constrain this upper limit. Every discovery of a neutron star, more massive than previous records, rules out softer equations of state and narrows the range of possibilities for what's inside. The current record holders, with masses around 2.1 to 2.35 solar masses, depending on measurement uncertainties, already tell us that the equation of state must be relatively stiff, at least at the densities achieved in these massive neutron stars. An interesting comparison can be made between neutron stars and particle accelerators like the Large Hadron Collider at CERN. The LHC collides protons at energies up to 14 trillion electron volts, recreating conditions similar to those fractions of a second after the Big Bang. These collisions allow physicists to study how quarks and gluons behave when they're briefly deconfined from protons. But there's a fundamental difference. LHC collisions last only about 10 to the minus 23 seconds, far too brief for equilibrium to be established. Neutron stars, in contrast, maintain extreme densities indefinitely, allowing matter to settle into its lowest energy state. In this sense, neutron stars probe different aspects of quantum chromodynamics than particle accelerators. They're complementary tools for understanding the strong nuclear force under extreme conditions. One of the most persistent misconceptions about neutron star interiors is that scientists have a clear, detailed understanding of the internal structure. Popular science presentations, including diagrams showing distinct layers labeled crust, outer core, inner core, and so on, can give the impression that we know exactly what's where. The reality is far more uncertain. While we're confident about the outer layers, the crust and outer parts of the core, the inner core remains deeply mysterious. We have theoretical models, some more plausible than others, but no definitive answers. This isn't a failure of science, it's an acknowledgement of the limits of our current understanding and an invitation to further investigation. The fact that 21st century physics still has fundamental mysteries about the nature of matter is actually quite exciting. The equation of state problem also connects to broader issues in physics. A complete theory of matter at nuclear densities requires understanding quantum chromodynamics in the non-perturbative regime, where standard calculational techniques break down. Solving this problem would advance our understanding of the strong nuclear force in general, with implications extending far beyond neutron stars. It might also shed light on the quark-gluon plasma that filled the universe microseconds after the Big Bang, and on the structure of atomic nuclei here on Earth. Neutron stars are natural laboratories for nuclear physics, allowing us to test our theories in regimes impossible to achieve artificially. What would happen if we could somehow bring a neutron star into a laboratory and study it directly? The answer is that we couldn't, not even in principle. Neutron star matter only remains stable under the immense gravitational pressure of the neutron star itself. Remove a piece of the core, and it would explosively decompress, releasing energy equivalent to thousands of nuclear weapons. As the neutrons and exotic particles decayed or rearranged into ordinary matter. This is why all our investigations must be indirect, inferring interior properties from external observations. It's like trying to understand what's inside a sealed box by shaking it, listening to how it sounds, watching how it moves, and measuring its weight without ever being able to open the box. Recent theoretical work has also considered the possibility of phase transitions within neutron star cores. Just as water can exist as ice, liquid, or vapor, depending on temperature and pressure, matter at nuclear densities might exist in different phases. There might be a sharp boundary between hadronic matter and quark matter, or the transition might be gradual with a mixed phase region where both types of matter coexist. If such phase transitions occur, they could have observable consequences. They might affect the star's rotation, create glitches in pulsar timing, or influence the gravitational wave signal from merging neutron stars. Some researchers have even speculated about the possibility of twin neutron stars, pairs of stars, with the same mass but different radii, due to different phases of matter in their cores. Have you ever wondered why this question matters beyond pure curiosity? Understanding neutron star interiors has practical implications for interpreting gravitational wave signals, for modeling supernova explosions, for calculating the synthesis of heavy elements in calonovae, and for testing fundamental physics theories. It's not just about what's inside one type of exotic object. It's about understanding how matter behaves at the extremes of density and pressure, knowledge that connects to some of the deepest questions in physics. Moreover, the fact that we can use astronomical observations to constrain theories of nuclear matter is a beautiful example of how different areas of science inform each other, astrophysics and nuclear physics working together to answer questions neither field could address alone. As we've explored the enigma at the heart of neutron stars, we've seen how even our most precise observations and sophisticated theories leave crucial questions unanswered. But this isn't a cause for frustration. It's an opportunity. Future observations with next-generation telescopes and gravitational wave detectors, combined with advances in nuclear theory and supercomputer simulations, will gradually constrain the possibilities, ruling out some models and strengthening others. Perhaps within a few decades, we'll have a definitive answer. Or perhaps neutron stars will continue to guard their deepest secrets, reminding us that the universe still has mysteries we're only beginning to unravel. Yet even as we grapple with what we don't know, we should take a moment to appreciate what we do know, and how these extreme objects born in violence and existing at the edge of physical possibility have already transformed our understanding of the cosmos and humanity's place within it. We've journeyed from violent births to dense matter, from cosmic lighthouses to warped space-time, from magnetic monsters to binary dances, from gravitational symphonies to mysterious cores. But now comes perhaps the most important question of all: why should any of this matter to us? We're talking about objects thousands of light years away, remnants of stars that died long before human civilization began exotic physics that seems impossibly removed from our daily lives. Yet neutron stars have already changed humanity in profound ways, and they promise to shape our future in ways we're only beginning to imagine. These cosmic extremes aren't just astronomical curiosities. They're tools for navigation laboratories for fundamental physics, and perhaps most importantly, reminders of our place in a universe far stranger and more beautiful than our ancestors could have dreamed. If this cosmic journey has moved you, inspired you, or simply made you think differently about the universe we inhabit, I'd be grateful if you'd hit that like button one more time and subscribe so we can continue exploring the wonders of space together. Let's start with something surprisingly practical: timekeeping and navigation. You might think the most accurate clocks humanity has ever built are atomic clocks, devices that use the precise oscillations of atoms to measure time. The best atomic clocks on Earth are astonishingly accurate, losing or gaining only about 1 second every 300 million years. But millisecond pulsars rival or even exceed this precision. These recycled neutron stars spun up to hundreds of rotations per second. By accreting matter from companions maintain such regular periods that we can predict their pulses years in advance to within microseconds. PSR J04374715, one of the closest and brightest millisecond pulsars, has been timed for over 25 years, with such consistency that it's considered one of nature's most perfect clocks. Why does this matter? Because a network of stable, precisely timed celestial beacons could revolutionize deep space navigation. Currently, spacecraft navigating beyond Earth orbit rely on radio communication, with ground stations constantly exchanging signals to determine position and velocity. This works well enough for missions to Mars or the outer planets, but it has limitations. The farther you go, the longer the communication delay becomes. By the time we're talking about missions to the outer solar system, or eventually to other stars, this method becomes increasingly impractical. But pulsars could provide an alternative. A spacecraft equipped with an X-ray telescope could observe multiple pulsars simultaneously, using their precise timing to triangulate its position anywhere in the solar system or beyond, without needing to communicate with Earth at all. This isn't just theoretical speculation. NASA tested this concept in 2017 and 2018 with the Sextant experiment, the Station Explorer for X-ray timing and navigation technology aboard the International Space Station. Using the NICER telescope we discussed earlier, Sextant demonstrated autonomous navigation by observing X-ray pulsars. The system successfully determined the space station's position to within about 5 kilometers, an impressive achievement for a proof-of-concept demonstration. Future versions could be far more accurate, potentially offering precision of a few meters anywhere in the solar system. Imagine interstellar spacecraft, centuries from now, navigating by the lighthouse beams of pulsars, using the same neutron stars we've been studying to find their way across the galaxy. It's a beautiful connection between pure astronomical research and practical application. Neutron stars also serve as unparalleled laboratories for testing fundamental physics. Einstein's general relativity has passed every test we've thrown at it for more than a century, from the precession of Mercury's orbit to gravitational waves from merging black holes. But physicists know general relativity cannot be the final word on gravity because it's incompatible with quantum mechanics at the deepest level. Somewhere in some regime we haven't yet probed adequately, general relativity must break down or require modification. Neutron stars provide some of the most extreme conditions in the universe where we might detect deviations from Einstein's predictions. The strong gravitational fields, rapid rotation, and intense magnetic fields create a testing ground where alternative theories of gravity might produce observable differences from general relativity's predictions. Binary pulsar systems are particularly valuable for these tests. The exquisite timing precision allows us to measure subtle effects like Shapiro delay frame dragging and orbital decay with extraordinary accuracy. The double pulsar PSR J0737-3039 has allowed tests of general relativity to better than 0.04% precision, and as observations continue over decades, this precision will only improve. We're probing relativistic effects in regimes where gravitational fields are millions of times stronger than anything in our solar system. If there are deviations from Einstein's theory, neutron star observations are among the most likely places to find them. So far, general relativity continues to pass with flying colors. But the search continues, and neutron stars remain our most powerful tools for the investigation. The study of neutron stars has also revolutionized our understanding of nuclear physics and the nature of matter. We discussed the equation of state problem at length, how we still don't know definitively what exists in neutron star cores. But this uncertainty has driven enormous progress in theoretical nuclear physics. Researchers have developed sophisticated computational techniques to calculate how nuclear matter behaves at extreme densities work that has applications beyond neutron stars. Understanding the strong nuclear force at high densities informs models of supernova explosions, nucleosynthesis, and the early universe. It connects to experiments at facilities like the Relativistic Heavy Ion Collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN, where physicists create tiny fleeting droplets of quark-gluon plasma, similar to what might exist in neutron star cores. There's a beautiful synergy here. Experimental nuclear physics informs theoretical models of neutron stars, which in turn suggests new experiments to perform. Astronomical observations constrain the equations of state, which guide laboratory research into nuclear matter. And advances in computational physics allow ever more sophisticated simulations that bridge the gap between theory and observation. Neutron stars have become a meeting ground where astrophysics, nuclear physics, and particle physics converge, each discipline informing the others in a virtuous cycle of discovery. Let's talk about something truly profound: neutron stars and the origin of elements. We mentioned earlier that the gold in your jewelry and the rare earth elements in your smartphone were forged in neutron star mergers. But it's worth dwelling on what this means. For most of human history, we had no idea where the material world around us came from. The elements seemed eternal and unchanging. Then in the 20th century, we learned that stars are nuclear furnaces fusing hydrogen into helium and building up heavier elements through the deaths of successive generations of stars. But this stellar nucleosynthesis couldn't explain everything. Elements heavier than iron require energy input to create. They can't be produced through normal stellar fusion. Where did these elements come from? The answer we now know is neutron stars. The extreme conditions during neutron star mergers with temperatures of hundreds of billions of degrees, densities exceeding nuclear density, and an abundance of free neutrons create the perfect environment for rapid neutron capture, the R process we've discussed. Atomic nuclei are bombarded with neutrons so quickly they don't have time to decay before capturing more neutrons, building up into the heaviest stable elements and even beyond into radioactive isotopes that later decay into stable heavy elements. This process occurs nowhere else in the universe with sufficient intensity to explain the abundance of heavy elements we observe. Every atom of gold, platinum, uranium, thorium, and dozens of other elements heavier than iron was forged in the collision of neutron stars billions of years ago. Think about what this means. You are made of stardust, but not just any stardust. The calcium in your bones came from supernova explosions. The iron in your blood was forged in the cores of dying massive stars. But some of the trace elements essential for life, like iodine in your thyroid gland, came from neutron star collisions. You are quite literally composed of the remnants of the universe's most extreme events, matter that has been through stellar cores, supernova explosions, and perhaps even neutron star mergers before eventually coalescing into planets and ultimately into you. Neutron stars aren't just abstract cosmic phenomena. They're directly connected to your existence and the existence of the technological civilization we've built. Can you imagine explaining this to someone from even a century ago? That we would understand not just that stars explode, but that we could observe these explosions across the universe, detect the ripples in space-time they produce, watch heavy elements being synthesized in real time, and connect all of this back to the composition of our own bodies. It's a remarkable achievement of human curiosity and ingenuity. We have taken a question as fundamental as what are things made of, and traced the answer back through billions of years of cosmic history to violent collisions between objects so extreme they challenge our understanding of matter itself. Looking toward the future neutron star science promises even more discoveries. The next generation of gravitational wave detectors will be sensitive enough to observe neutron star mergers throughout most of the observable universe. Every detection will provide more data about the equation of state, help us understand the diversity of neutron star properties, and potentially reveal entirely new phenomena we haven't predicted. Future radio telescopes like the Square Kilometre Array, currently under construction in Australia and South Africa, will be able to detect and time thousands of new pulsars, many in exotic systems we haven't encountered before. Some of these might be in triple star systems, or orbiting black holes, or exhibiting behaviors we haven't yet imagined. Each discovery will be an opportunity to test physics in new regimes. Space-based missions will also advance neutron star science dramatically. LISA, the Laser Interferometer, space antenna scheduled for launch in the 2030s, will detect gravitational waves at lower frequencies than ground-based detectors can access. While LISA is primarily designed to observe supermassive black hole mergers, it might also detect gravitational waves from deformed or oscillating neutron stars, providing yet another window into their properties. Enhanced X-ray observatories will allow more detailed studies of neutron star surfaces, magnetic fields, and accretion processes. Gamma-ray telescopes will help us understand magnetar outbursts and the connection between neutron stars and fast radio bursts. There's also the exciting possibility of detecting neutrinos from nearby neutron stars. Neutrinos are ghostly particles that barely interact with matter passing through the Earth, as easily as light passes through a window. But they carry information about processes happening deep inside astronomical objects, information that escapes before light does, because neutrinos aren't absorbed by overlying material. The detection of neutrinos from supernova, 1987A, a supernova in the Large Magellanic Cloud, marked the birth of neutrino astronomy. Future neutrino detectors might be sensitive enough to observe signals from neutron star cooling or from accretion processes, providing yet another messenger to complement electromagnetic observations and gravitational waves. One of the lessons neutron stars teach us is humility. For all our scientific progress, for all the sophisticated instruments we've built, and the elegant theories we've developed, we still can't definitively answer basic questions like, what's in the core of a neutron star? This isn't a failure, it's an acknowledgement that the universe is complex and that some mysteries require generations of effort to unravel. It's also a reminder that there's always more to discover, that no matter how much we learn, nature always has surprises waiting. The universe is far stranger and more intricate than we imagine, and neutron stars exemplify this beautifully. They exist right at the edge of what physics allows, embodying extremes of density, gravity, magnetism, and energy that push our theories to their limits. But perhaps the most important legacy of neutron star research is what it represents about human nature. We're a species that looks up at the night sky and asks questions. Why are the stars there? What are they made of? How do they work? These questions have no immediate practical value. Our ancestors survived perfectly well without knowing about nuclear fusion or general relativity. Yet, we couldn't stop ourselves from wondering, from building ever more sophisticated tools to probe the cosmos, from developing mathematical frameworks to make sense of what we observed. The study of neutron stars is pure curiosity-driven research at its finest, asking fundamental questions about the nature of reality, simply because we want to know the answers. And yet, as we've seen, even the purest research often yields unexpected practical benefits. Pulsar navigation tests of fundamental physics, insights into nuclear matter, understanding of element synthesis. All of these emerge from studying objects we can never visit, will never touch, and discovered initially by accident while looking for something else entirely. This is why curiosity-driven research matters. We can't predict which investigations will lead to transformative applications, because the connections often aren't obvious until decades later. Supporting science, even science that seems impossibly abstract, is an investment in humanity's future understanding and capability. Neutron stars also remind us of our place in the cosmos. We live on a small planet orbiting an average star in an unremarkable galaxy. The universe contains hundreds of billions of galaxies each, with hundreds of billions of stars, many of which will eventually die and leave behind neutron stars or black holes. In this vast cosmic arena, humanity's entire existence is a fleeting moment. The neutron stars we observe today were born long before humans walked the Earth, and they'll continue shining their lighthouse beams long after human civilization has ended, assuming we don't spread to the stars ourselves. This cosmic perspective can be humbling, even overwhelming, but it can also be inspiring. We're part of this universe made of its matter, subject to its laws. And unlike the mindless stars and galaxies, we can understand it. We can look out at neutron stars spinning hundreds of times per second with magnetic fields strong enough to warp space-time, and we can comprehend what's happening. We can write down equations that describe their behavior and make predictions that observations confirm. This is extraordinary. As we approach the end of our journey through the realm of neutron stars, let's take a moment to reflect on what we've discovered together. We've watched massive stars collapse in less than a second, compressing matter to densities that erase the distinction between atoms. We've explored the exotic states of matter that exist inside these cosmic spheres, from iron crystal crusts to nuclear pasta to possibly deconfined quark matter in the core. We've learned how these dead stars become cosmic lighthouses, spinning at impossible speeds and sweeping beams of radiation across the galaxy. We've seen space-time itself bend and twist around them, with time flowing slower and light taking curved paths through warp geometry. We've witnessed the fury of Magnetaire's objects, with fields strong enough to warp the quantum vacuum. We've observed the violent interactions of binary systems, where neutron stars consume their companions, or spiral together in dances that end in catastrophic mergers. We've listened to the universe through gravitational waves, feeling the ripples from collisions that occurred millions of years ago and halfway across the cosmos. And we've grappled with the mysteries that remain the questions about what really exists at the heart of these objects that our current science cannot yet fully answer. Each of these topics could fill a lifetime of study. Researchers dedicate entire careers to understanding specific aspects of neutron star physics, and they do so gladly because these objects are endlessly fascinating. But even as specialists dive deep into particular questions, the broader story remains inspiring and accessible. You don't need a physics degree to appreciate that neutron stars are matter pushed to the edge of reality existence at the very limits of what the universe permits. You don't need to understand tensor calculus to marvel at objects that make time flow differently, or that ring space-time like a bell when they collide. The universe is amazing, and neutron stars are among its most amazing constituents. So, what's next? Where does neutron star science go from here? The honest answer is that we don't know, and that's exciting. Every new gravitational wave detection, every newly discovered pulsar, every improvement in our theoretical understanding has the potential to surprise us. Maybe we'll definitively determine what's in the core of a neutron star within the next decade. Maybe we'll discover entirely new classes of neutron stars with properties we haven't predicted. Maybe we'll detect signals that challenge our current theories and force us to revise our understanding. Or maybe the mysteries will deepen with each answer, raising 3 new questions. Whatever happens, it will be fascinating to watch. And everyone who studies neutron stars knows they're privileged to work on such profound questions. I want to thank you for joining me on this journey through one of the universe's most extreme phenomena. We've covered a lot of ground, from the births of neutron stars to their ultimate fate from the smallest scales of nuclear matter to the cosmic scale of gravitational waves propagating across the universe. I hope this exploration has given you not just facts and information, but a sense of wonder about the cosmos we inhabit. The universe is vast and ancient and strange, filled with phenomena that challenge our imagination. Neutron stars spinning hundreds of times per second, magnetic fields quadrillions of times stronger than Earth's matter compressed to nuclear density, gravitational waves rippling through space-time. All of these are real. They exist out there right now, and humanity has developed the capability to observe and understand them. If you found this journey through the cosmos worthwhile, please consider subscribing to this channel. There are so many more stories to tell, so many more corners of the universe to explore together. From the quantum realm to the largest structures in the cosmos, from the Big Bang to the ultimate fate of the universe, science gives us windows into realities beyond our everyday experience. And I'd love to continue sharing these discoveries with you, unpacking the complex into the comprehensible and hopefully inspiring the same sense of wonder that drives scientists to dedicate their lives to understanding the universe. Until our next cosmic exploration, keep looking up at the stars. Some of those points of light are neutron stars, stellar corpses announcing themselves, with pulses of radiation spinning at impossible speeds, warping space and time around them. They've been there for millions or billions of years, and they'll continue long after we're gone. But for this brief moment in cosmic history, we're here to observe them, to understand them, and to appreciate the universe's extraordinary capacity for creating phenomena at the absolute edge of physical possibility. That's a privilege worth celebrating. Thank you for spending this time with me, for letting me share these wonders with you. Stay curious, keep questioning, and I'll see you in the next chapter of our cosmic journey. The universe has countless more stories to tell, and we've only just begun.